Hello there, and welcome to Life Beyond Scene, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we're heading somewhere that usually feels like the farthest edge of the world, a place we picture as endless white, sharp wind and silence so cold it almost sounds loud. Antarctica. But we're not visiting the Antarctica, you know. We're going back to a version of it that feels almost impossible. A version that existed while one of the most famous predators in Earth's history was alive and moving through the oceans. Megalodon. A shark so large it makes modern great whites look like they're still in training. And if that image sounds strange, a giant shark near Antarctica, it should. Because it means the world was different. The water was different. The coastlines were different. Even the air would have felt different on your skin. So as you settle in, let me ask you something gentle and simple. Where are you listening from tonight? And what time is it for you right now? Somewhere out there you might be hearing this in the early hours of the morning, or maybe it's still evening and you're letting the day loosen its grip. Either way, I'm glad you're here. And if you find this kind of slow, soothing science comforting, if you like drifting through deep time with a calmer mind, I'd be grateful if you liked the video and maybe subscribed. It helps this little quiet corner reach more people who could use a peaceful place to land. Now, take a breath. Let your shoulders drop. Let the room around you fade just a little. Because we're about to step into an ancient southern ocean when Antarctica wasn't a frozen fortress yet, and something enormous could have been moving beneath the surface, unseen, unbothered, and perfectly at home. Most people imagine Megalodon in tropical waters, warm, bright, full of life, the kind of ocean you could swim in without your body complaining immediately, and to be fair, that's not a bad instinct. Megalodon lived during a time when many parts of the world were warmer than they are today. It existed mainly during the Miocene and into the Pliocene, roughly between about 23 million and 3.6 million years ago, depending on how you define its full range. And during a good part of that span, Antarctica was not the solid block of ice we picture now. It had ice, yes. It wasn't a beach holiday. But it wasn't the endless white continent we know either. It was in the middle of a long transformation, a slow shift from something that could support more open land and more varied coastlines, into the locked glacial world we recognise today. To understand what Antarctica was like while Megalodon was alive, we have to do something our brains don't always enjoy. We have to stop using the modern world as the default setting, because modern Antarctica makes us assume the past was always like this. Cold, harsh, frozen. A place where only the toughest animals survive. A place that feels like it belongs more to machines and research stations than to ecosystems. But Antarctica has had many lives. There were times in the distant past when Antarctica had forests, real forests, trees, leaves, soil that wasn't crushed under kilometres of ice. There were periods when it was connected to other land masses, when it wasn't as isolated as it is now. There were eras when the southern ocean currents hadn't formed the same way, when warm water could reach further south, and when seasonal patterns were different. By the time Megalodon arrived on the scene, Antarctica had already been cooling for a long time. The biggest steps toward a permanently icy continent began earlier, especially around the Eocene-Oligocene transition, about 34 million years ago, when Antarctica started to build large ice sheets. But that doesn't mean it became instantly frozen in the way we see today. Ice grows and retreats, climate shifts in pulses, the ocean and the atmosphere take time to settle into new patterns. And during the Miocene, the world was still capable of surprising warmth, even at high latitudes. So picture Antarctica not as a single image, but as a changing place. Sometimes more ice, sometimes less. Sometimes coastlines exposed, sometimes buried. Sometimes seas with more life. Sometimes seas tightening into colder systems. Now, imagine the Southern Ocean during that time. It wouldn't have been empty, not at all. Even today, Antarctic waters are full of life. It just tends to be life that thrives in cold, nutrient-rich conditions. Krill, penguins, seals, whales. Fish adapted to freezing temperatures. a whole food web built around productivity that blooms when the conditions are right. Back in the Miocene, the cast of characters was different, but the ocean was still an engine of life. There were early whales in many forms. Some were smaller, some were strange compared to what we know now. Some still carried traces of their land-walking ancestors in their anatomy, even if those traces were fading with time. There were seals and seal-like animals evolving into their own niches. There were fish species that no longer exist, and others that were early versions of lineages we still have today. And most importantly for our story, there was food. Big food. Because Megalodon wasn't built to chase small snacks. It was built for large prey, thick-bodied prey. Prey with blubber, muscle, and enough energy to make the chase worth it. And the Miocene was a strong time for whales. Whale diversity expanded. Many groups of whales were evolving and spreading. That means there were plenty of targets for a giant predator that specialised in taking down marine mammals. So could Megalodon have been near Antarctica? It's possible that it moved into cooler waters at times, especially if the climate allowed it. Fossil evidence for Megalodon tends to be found more often in warmer regions, but absence of evidence is not always evidence of absence. Fossils are picky. They only form under certain conditions. They only survive if geology cooperates. They only get found if someone looks in the right place and recognises what they're holding. The bigger point is this. The Southern Ocean during the Miocene was not automatically too cold for large marine predators. It wasn't the same as today's polar environment, and even today, large predators move through cold waters if the ecosystem supports them. So instead of imagining Megalodon as a creature trapped in tropical postcards, imagine it as a traveller of opportunity, a predator that followed prey, a predator that moved along coastlines and continental shelves, a predator that didn't care about our assumptions. Now, let's step closer to the Antarctic coastline of that time. Modern Antarctica is ringed by ice shelves and steep, frozen edges. Much of its land is buried. The coastline is partly hidden by ice, and what you see depends on the season and the region. In many places, the boundary between land and sea is not a sandy beach or rocky shore. It's ice meeting water. But during warmer stretches of the Miocene, the shape of Antarctica's coast could have been more open in places. There could have been more exposed land along the edges, more bays, more shallow shelves not sealed under thick ice, more room for ecosystems to spread out in the shallows. Shallow seas are important. They're often where the ocean produces the most life. Sunlight reaches the bottom more easily. Nutrients mix. Food chains build up. And where food chains build up, predators show up. If you stood on a rocky outcrop in Miocene Antarctica, you might have seen a coastline that looked rough, wet, and alive. Not warm like the Mediterranean, not gentle like a quiet lake, but alive. The air would still be cold by many standards, but not necessarily deadly in the same way. Depending on the exact time period, temperatures could have been higher than today, especially in coastal regions. There were still long days and long nights because the continent was still near the pole. The sun still behaves strangely compared to most places on Earth. That means the light itself would have felt unusual. You could have a day that seems to last forever, with the sun circling low and refusing to fully set. Or you could have long darkness, a slow season where the sky stays dim and the land feels like it's holding its breath. This matters for the ocean too because sunlight drives surface productivity. When the sun stays up longer, algae and plankton can bloom in big waves feeding everything else. When the light fades, the surface changes. Life shifts deeper or slows down. So Antarctica would still have had strong seasonal rhythms, even if the climate was warmer overall. Now think about the water. The Southern Ocean is famous today for its cold, powerful currents. One of the biggest players is the Antarctic Circumpolar Current, a massive flow of water that circles the continent and helps keep it isolated. It acts like a barrier, limiting the amount of warm water that can reach Antarctica from the north. This current is part of why Antarctica is so cold now. It helps maintain the continent's frozen state. But the Antarctic Circumpolar Current did not always exist in the form it has today. It developed as tectonic shifts opened ocean gateways, especially the Drake Passage between South America and Antarctica, and the Tasman Gateway between Antarctica and Australia. As these gateways opened, ocean circulation patterns changed. Water could flow around Antarctica more freely. The current strengthened. Isolation increased. Cooling increased. During Megalodon's time, this system was already developing, but it wasn't necessarily identical to today's full-strength version. Ocean circulation was still evolving, and even small differences in currents can change climate patterns, nutrient distribution, and where life thrives. So the Miocene Southern Ocean could have been a mix of cold currents and warmer intrusions, depending on the period and the region. That creates a world that is not uniform. Some parts could have been colder, more like the modern Antarctic environment. Other parts could have been milder, especially in shallow coastal areas during warmer phases. This kind of patchwork environment can support a wider range of animals than a fully locked, uniformly frozen system. Now imagine swimming through those waters, just for a moment. Not you personally, because you'd last about as long as a dropped ice cube in a frying pan. But imagine the feeling of it. The water would have been heavy, dense, cold enough to tighten muscles, the kind of cold that makes every movement feel slower. But not necessarily freezing at the surface all year round. It would have had a certain colour, not the bright tropical turquoise people post online, more like deep green, steel blue, grey blue depending on the light, a sea that reflects clouds and fog and low sun angles, a sea that looks serious. And in that water, life would have been moving constantly. Schools of fish, some small, some larger. Early penguin relatives perhaps along the coasts. Seals hauling out when they could. Whales moving through migration routes. Smaller sharks, larger sharks. And somewhere farther out in deeper water, something enormous. Megalodon is known mostly from its teeth. That's what we have. Teeth the size of your hand, thick, triangular, serrated, built for cutting through flesh and bone. And from those teeth, scientists estimate body sizes that could reach around 15 to 18 meters, sometimes more depending on the model and the specimen. That's longer than a bus. It's the kind of size that changes the rules of the ocean around it. A creature like that doesn't need to rush. It doesn't need to dart around like a smaller shark. It can move steadily. It can conserve energy. It can let the environment come to it. It can pick moments. If Megalodon entered Antarctic waters, it would have been following something worth the trip. Likely whales, likely large marine mammals moving through feeding grounds. And the Southern Ocean has always been a feeding ground. Cold water holds more oxygen. Nutrient mixing can be intense. Upwelling brings food from deeper layers. That supports large animals. So even though we often associate warm water with abundance, cold seas can be extremely productive. The kind of productivity that builds bodies big enough to feed something like Megalodon. Now picture the hunting, not a dramatic chase with constant speed and splashing. Real predation often isn't like that. Real predation can be quiet, patient, based on timing. A giant shark can approach from below. The deeper water is darker. Light fades fast. From above, the surface might look calm, even if waves are moving. A whale might be travelling with others, or it might be alone. It might be young. It might be sick. It might be distracted. It might be feeding. And then the water changes. Not because the whale sees something, but because the environment shifts around a moving mass. A large predator displaces water. It changes pressure. It creates a subtle movement that smaller animals might sense before the prey does. Megalodon likely attacked with force aimed at disabling. There's evidence that it targeted fins and tails. If you break a whale's ability to swim properly, the fight becomes short. A whale that can't move well becomes a whale that can't escape. This is not a pleasant image, but it's part of what the ocean is. The ocean is not gentle, it's balanced, but it's not kind. Predators are part of the system. Without them, ecosystems collapse in different ways. So if Megalodon was present, it would have been part of the balance of that ancient Southern Ocean, and the scene around it would have been busy, even if it looked quiet from above. Birds would circle, smaller scavengers would wait, fish would gather at a distance, the ocean would recycle energy the way it always does. Now, let's zoom out a little, because Antarctica wasn't only ocean. There was land, and the land was changing too. By the Miocene, much of Antarctica was cooling, but there were still regions that could have supported patches of vegetation in some coastal areas, especially during warmer intervals. Not palm trees, not jungles, but plants that can survive cooler conditions. In earlier times, Antarctica had been much greener, with forests. By Megalodon's time, that greenness was reduced, but it wasn't necessarily gone everywhere in the same way, and the coastline itself would have looked different. Without the same massive ice coverage, the shapes of bays and inlets could have been more exposed. The land would have had rocky areas, sediment deposits, and places where rivers could run during warmer seasons. Rivers matter because rivers carry nutrients. They bring minerals and organic material into the sea. That boosts productivity along coasts, so you can imagine a coastline where meltwater streams ran seasonally, where muddy plumes entered the ocean, where plankton bloomed in response, where fish gathered, where whales followed. Everything connects. Now let's talk about the sky, because the sky over Antarctica has always been part of the experience. Even in a warmer Miocene climate, you would still have weather that feels intense, strong winds, fast changes, fog that rolls in like a curtain, storms that build over open water and slam into the coast. The Southern Ocean is notorious for storms even now. There's a reason sailors have respected those latitudes for centuries. The winds have room to run around the globe, waves can build, systems can spin without much interruption. So Megalodon's world near Antarctica would have included heavy seas at times. Not always calm hunting conditions, not always gentle travel. But large animals can handle rough water better than small ones. Rough water can even help predators by reducing visibility. It can break up sound. It can confuse prey. And the light would be strange because of latitude. In summer, the ocean surface might glow for hours. In winter, it could feel like the day never fully arrives. That means the rhythms of feeding and movement could be different. Animals might take advantage of long daylight to feed heavily, or they might use the dim seasons to move with less exposure. Megalodon, being a shark, would have relied on senses that don't need sunlight. Sharks detect electrical signals, they detect movement, they smell, they feel pressure changes. They don't need clear visibility to be effective, so in a way, a dim, cold sea could have been a comfortable hunting ground. Now there's another piece to this story, one that matters if we're going to understand what Antarctica was like in that era. The planet was in transition. The Miocene began relatively warm compared to later periods. There was even a time called the Miocene climatic optimum, around 17 to 15 million years ago, when global temperatures were higher. Antarctica had less ice than today during that warm stretch. Then cooling resumed, ice expanded, the world moved toward the colder patterns that would define later epochs. So if you could watch Antarctica across Megalodon's lifetime as a species, you'd see it shifting, not overnight, not dramatically from one year to the next, but gradually, steadily, with occasional jumps. You'd see more ice forming, more seasonal freezing, more permanent ice in certain regions. You'd see coastlines becoming harder. You'd see ecosystems adapting or moving. And that matters for Megalodon too, because Megalodon didn't survive forever. By the end of the Pliocene, Megalodon disappeared. We don't have one single agreed reason. It was likely a combination. Cooling oceans reduced suitable habitat. Sea levels changed. Prey populations shifted. New predators emerged, including early versions of modern great white sharks and other large predators. Whale species changed. Migration routes changed. The balance moved. And a predator that depends on large prey and certain conditions can struggle when the world tightens around it. So Antarctica's transformation into a colder, more isolated continent may have been part of the larger story of why Megalodon eventually faded away. But while it was alive, Antarctica was not the silent ice kingdom we picture. It was a place with movement, a place with food webs, a place with currents and coastlines and storms and long, strange light. And somewhere in that ancient southern ocean, there may have been moments when the water held something so large that even the whales adjusted their paths without knowing why. Now, as we continue, we'll drift deeper into that world. We'll stay close to the water, and we'll build the picture slowly, piece by piece. We'll look at what the coastlines likely looked like, what kinds of animals shared those seas, how hunting might have worked in colder currents, and how the slow arrival of stronger ice changed everything around it. For now, just let the image settle in your mind. Not a frozen continent, but a changing one. Not a tropical sea, but a productive one. Not a monster story, but an ecosystem story. A real planet, in a real phase of its life, when Antarctica was still becoming itself, and Megalodon was still out there somewhere, moving through the water like a quiet shadow with teeth. And as we drift a little farther into that ancient southern world, it helps to start with the simplest question of all. What did it actually feel like to be there? When people hear Antarctica, the mind tends to snap to a single image. A continent sealed in ice, a horizon of white and blue, wind sharp enough to make your eyes water, snow that squeaks underfoot like it's trying to complain. Even the word itself feels cold. Antarctica. It sounds like it should come with a blanket. So when someone says Antarctica but in the time of Megalodon, it almost feels like a trick. Like someone is trying to mix two different movies into one scene. A giant prehistoric shark, the kind you picture in deep, warm oceans, and a continent that today is so cold it can preserve a fallen meteorite like it's a museum display. But the truth is, Antarctica has not always been the frozen fortress we know, and the time when Megalodon was alive, mostly during the Miocene and into the Pliocene, was part of a long, slow transformation. Antarctica was already cooling compared to its much warmer ancient past, but it wasn't locked into its modern deep freeze in the same way. If you could step back into that era and feel the air, you might be surprised by what your body notices first. Not warmth like a summer afternoon, not the kind that makes you want to open a window and smell flowers, but a softness, a lack of the brutal edge we associate with Antarctica now. It would still be a high-latitude world. The light would still behave strangely. The seasons would still feel dramatic. But the overall climate, especially in certain periods of the Miocene, could have been milder than most people imagine. To understand why, it helps to stop thinking of climate as a single thermostat setting and start thinking of it as a system of moving parts. Ocean currents, atmospheric circulation, greenhouse gases, the shape of continents, the height of mountains, and the way ice reflects sunlight back into space. All of these pieces interact, and when they shift, the whole planet can feel different. During Megalodon's time, the Earth was not the same temperature as today. Not everywhere, not consistently, but on average the planet was warmer in many stretches. There were intervals where global temperatures rose enough to reduce polar ice, expand forests in some regions, and change sea levels. One of the most important warm phases during the Miocene is often called the Miocene climatic optimum. It happened roughly around 17 to 15 million years ago. During that time, global temperatures were higher than they are now, not because the sun suddenly got brighter, not because the Earth moved closer to it, but because the balance of gases in the atmosphere and the arrangement of the oceans and continents created conditions that trapped more heat. Carbon dioxide levels were higher than modern pre-industrial levels, and that matters. Carbon dioxide acts like a blanket in the atmosphere. It lets sunlight in, but it slows down the escape of heat back into space. It doesn't create heat from nothing, but it changes how long the heat stays around. When the planet holds onto more heat, the poles feel it strongly. Polar regions are sensitive because of feedback loops involving ice. Ice reflects sunlight. It's bright and reflective, so it bounces a lot of energy back into space. But when ice shrinks, darker surfaces like ocean water or bare ground get exposed. Dark surfaces absorb more sunlight, which leads to more warming, which leads to less ice, and so on. That means once warming begins, the poles can change faster than you might expect. So in the warmer stretches of the Miocene, Antarctica could have had less ice volume than today, and in some coastal regions, conditions could have allowed more exposed land and more open water. Now this doesn't mean Antarctica was tropical. It doesn't mean you'd see palm trees swaying in a warm breeze while Megalodon cruised past like a tourist attraction. It means the climate was different enough that the story of Antarctica was still being written, and that story is easier to picture when you focus on the coastline. Coastal climates are often moderated by the ocean. Water holds heat longer than land does. It warms slowly and cools slowly. That makes coastal areas less extreme than inland areas, especially on large continents. Even today, coastal regions can be far less severe than the interior, depending on currents and winds. In the Miocene, parts of Antarctica's coastal environment could have been less locked in ice than they are now. There may have been areas where seasonal melting happened more widely, where ice shelves were smaller or less stable, and where the sea had more access to the land. This matters because ice coverage changes the entire personality of a place. When a coastline is buried behind ice, the land-sea boundary becomes a wall. It limits where animals can haul out. It limits where plants can grow. It changes sediment flow. It changes nutrient input. It changes everything. But if that boundary is more open, even in patches, the ecosystem becomes more complex. You get shallow waters with more light. You get more coastal productivity. You get more variety in habitats. And in the ocean, variety is opportunity. Let's talk about the water temperature itself, because that's usually what people are really wondering about. Could Antarctic waters have been warm enough for something like Megalodon? First, we should be careful with the word warm. Warm compared to what? Warm compared to modern Antarctic waters, which can hover near freezing, often around 2 to 2 degrees Celsius depending on salinity and conditions. Warm compared to tropical seas, which can sit comfortably in the mid to high 20s Celsius. Warm compared to a human's comfort zone. Miocene Southern Ocean temperatures would have varied by region and by time. They were influenced by global climate and by ocean circulation patterns. In warmer phases, surface waters could have been higher than today. Not necessarily warm like a bath, but less hostile. Even a few degrees can change the entire system. If the surface water is slightly warmer, sea ice forms later in the season and melts earlier. That gives marine life more time to feed and grow. It allows animals to migrate further south. It changes which species can tolerate the conditions, and for a large predator like Megalodon, what matters isn't whether a human would enjoy swimming there. What matters is whether the environment supports prey, and whether the predator's biology can handle the conditions. Megalodon was a shark, and sharks are often associated with warm water, but not all sharks avoid cold seas. Some modern sharks move into colder waters, especially if food is present. Great white sharks can be found in cooler temperate waters. Sleeper sharks live in cold, deep environments. Sharks have strategies for dealing with temperature. There is also ongoing debate about how Megalodon regulated its body temperature. Some research suggests it may have had some degree of regional endothermy, meaning parts of its body could stay warmer than the surrounding water, similar to some modern sharks and tuna. That doesn't make it warm-blooded in the mammal sense, but it could allow it to function better in cooler waters than a fully cold-blooded fish would. If Megalodon could maintain higher muscle temperature, it would have had an advantage in a range of environments. It could have hunted effectively in cooler regions, followed prey farther, and used different parts of the ocean. So it's not unreasonable to imagine Megalodon moving into higher latitudes at least seasonally, especially during warmer intervals, especially if prey was abundant. Now, consider the prey. During the Miocene, whales were diversifying. Many groups were spreading and evolving. Some whales were becoming larger. Some were experimenting with different feeding strategies. Some were moving into new habitats. Whales are a powerful reason for any large predator to show up, because whales are mobile packages of energy. A whale is muscle, blubber, blood, and heat. It's a moving feast, but also a dangerous one, and whales don't exist in empty oceans. Where whales feed, there are fish, krill, squid, and all the smaller things that make the food web work. So if Miocene Antarctica had productive waters with whales feeding in them, it could have been a place that attracted large predators, even if only at certain times. And here's where the idea of warmer than you'd expect becomes important. It's not only about temperature numbers, it's about how the world felt compared to what we assume. If you were standing on a Miocene Antarctic shore, you might not see an endless frozen plateau. You might see exposed rock, wet ground, a coastline shaped by waves instead of ice walls. You might see seasonal meltwater streams cutting through sediment. You might see fog rolling in from the sea instead of a constant blizzard. The air could still be cold, you'd still want a coat, but it might not feel like instant punishment. You might hear birds, not the same species we have now, but the idea of coastal bird life is not far-fetched. You might see signs of life in the water, dark shapes surfacing, spray from a whale's breath, ripples from something moving just beneath the surface, and the ocean itself would not be quiet in the way people imagine polar oceans. It would be noisy, wind and waves, ice cracking in the distance during colder seasons, animal sounds, the low exhale of whales, the splash of bodies surfacing and diving. A warmer world also means sea level changes. When global temperatures are higher and ice is reduced, sea levels tend to be higher. That can flood coastal areas, create shallow seas, and expand continental shelves. Shallow seas are important because they are often rich feeding grounds. They can support large populations of fish and marine mammals. They are also easier for large predators to patrol because prey tends to gather there. So a warmer Antarctica could have meant more accessible coastal habitat, more shallow marine environments, and more biological activity along the edges of the continent. Now, we should also talk about the idea of isolation. Modern Antarctica is isolated by powerful ocean currents, especially the Antarctic circumpolar current, which circles the continent and helps keep warm water from moving south. But during the Miocene, this system was still developing. The gateways between continents were opening and shifting. The flow patterns were changing. Even if the circumpolar current existed in some form, its strength and structure may not have been identical to today. And that means warm water could have had different pathways to reach the south, at least intermittently. Ocean currents are like conveyor belts. They move heat around the planet. They move nutrients. They move life. If currents allowed warmer water to reach certain Antarctic regions more often, it would have made those areas less icy and more biologically active. At the same time, colder currents could still exist. Antarctica wouldn't be uniformly mild, it would be a patchwork. Some areas more open, some more frozen, some seasons more harsh, some less. And that patchwork creates ecological edges, and ecological edges are often where life thrives. In nature, boundaries are busy, where cold meets warm, where deep meets shallow, where currents mix. Those are places where nutrients concentrate and prey gathers. So even if Antarctica wasn't warm, it could still have been a place with rich feeding zones along the continental shelf and in coastal waters. Now let's zoom out even more and picture the world map of that time. The continents were in roughly similar positions to today, but not exactly. The ocean gateways were different. The climate belts were different. The ice sheets were different. The world had fewer modern constraints. It had more flexibility. And when the world is warmer overall, it changes the migration patterns of animals. It changes where whales go. It changes where fish populations concentrate. It changes where predators can follow. Megalodon likely didn't live in one spot forever. It probably moved. It likely followed prey migrations and breeding routes. It likely used nursery areas in warmer, shallow waters, because young sharks often need safer, productive environments. If Megalodon had nursery areas in warmer regions, adults could still roam far from those nurseries. Many large marine animals do that. They have certain areas for breeding or raising young, and other areas for feeding. So the idea of Megalodon appearing in higher latitudes is not as strange as it first seems. It becomes a matter of timing, climate, and opportunity. Now, imagine the sensation of being on the water in that time. You're not in a small modern boat with GPS and a warm jacket made of synthetic fabric. You're just there, in the open air, in a world with no human noise, no engines, no distant city hum, no aircraft overhead. The ocean surface moves in long swells. The sky is low and heavy with cloud. The light is pale, stretched out, because the sun sits at an angle that makes shadows long even at midday. You can smell salt, cold water, and something organic. The smell of life in the sea. The smell of algae and wet rock. The smell of something feeding somewhere beyond your sight. You see a dark line on the horizon that could be land or could be fog. You see birds cutting across the wind. Then you see a blow, a sudden burst of mist from a whale surfacing. Then another. Then another. The whales are there because the water is productive. They're feeding. They're moving slowly, not sprinting. They're taking advantage of a place that provides enough food to make the journey worth it, and beneath them, the water is deep. The surface looks like one layer, but it isn't. Below the surface, there are temperature gradients, currents sliding past each other, zones of light and darkness, and in the deeper layers, something large can move without being seen. A shark like Megalodon wouldn't need to circle dramatically. It wouldn't need to break the surface. It could approach from below, using the darkness as cover. Even in a warmer Miocene Antarctica, the water would still get dark quickly with depth. Light doesn't travel far in the ocean, especially in water rich with plankton and particles. So you could have a surface that looks calm enough, with whales feeding, and below them, an animal the size of a truck moving quietly through the dim water. That's part of what makes this setting so unsettling and so fascinating. It's not a fantasy world, it's a real Earth in a different mood. Now, let's clear up one more misunderstanding people often have. A warmer Antarctica doesn't mean a stable, comfortable Antarctica. Warm periods in Earth's history often come with intense weather patterns. When the atmosphere holds more heat, it holds more energy. That can mean stronger storms, more dramatic rainfall patterns, and more powerful wind systems. The Southern Ocean is already one of the stormiest places on Earth. In a warmer climate, it could still be stormy, possibly even more active in some ways. So this would not be a gentle place. It would be a place of movement and force. The ocean would still be capable of violence. But life doesn't require gentleness. It requires opportunity. If there was enough food, enough open water, and enough suitable habitat, animals would thrive, even in rough conditions. That's why it's so important to separate warm from easy. A world warmer than you'd expect could still be challenging. It could still be harsh. It could still demand adaptation. It would just be different from the modern image of Antarctica as a frozen desert. And that difference is what allows the idea of Megalodon in the southern seas to feel less like a cartoon and more like a possibility. Now, if you're wondering what Antarctica looked like above the water in that time, you're not alone. The land matters. The shape of the coast matters. The presence or absence of ice matters. Because the next step in understanding this world is to stop thinking of Antarctica as a finished product. It wasn't finished yet. It was still becoming the continent we know. Ice was still expanding and retreating. Currents were still settling into patterns. Ecosystems were still adjusting. And when a place is in transition, it can host combinations of life that seem strange from a modern perspective. A giant shark in southern waters. Whales feeding in seas that are cooling but still productive. Coastlines that shift between open rock and creeping ice. This is a world in motion. And as we drift deeper into it, the next thing to do is to take a closer look at Antarctica itself. Not just its temperature, but its identity during that era. What it was before it became the Ice Kingdom. What kind of continent it was trying to be. Because once you see that, the rest of the picture starts to make sense. When we picture Antarctica today, we picture certainty. A continent that feels settled into its role. Ice on top, ice at the edges, ice in the air, ice in the very idea of it. a place that doesn't seem like it ever had a choice, as if it was born frozen, stayed frozen, and will always be frozen, no matter what the rest of the world does. But Antarctica wasn't always like this. It wasn't always the Ice Kingdom. And when Megalodon was alive, Antarctica was still in the middle of becoming the version we know. It had already changed a great deal compared to its far older, greener past, but it hadn't reached the final locked state that defines it now. It was a continent with a long memory and a shifting face, a place where the land, the ocean, and the climate were still negotiating what normal would mean. To understand Antarctica before the Ice Kingdom, we need to let go of the idea that ice was always the main character. For much of Earth's history, Antarctica played other roles. It was a land of forests. It was part of a connected world. It sat in a different climate system, under a different sky, with different animals moving through its waters and across its ground. It helps to start with the simplest truth about Antarctica. It is a continent, not a giant iceberg, not a permanent snowfield, not an abstract symbol of cold. It's rock, mountains, valleys, coastlines, rivers that once ran freely, and basins that now hold ice thick enough to bury entire landscapes. If you could peel away Antarctica's ice like a lid, you'd find a continent with real geography. Mountain ranges, including the Transantarctic Mountains, which divide East and West Antarctica. Volcanic regions, including Mount Erebus, which is still active today. Deep basins and hidden valleys carved by ancient forces. That geography matters because it shaped how ice formed, where it formed, and how it moved. But before ice became the defining feature, Antarctica's geography supported other ecosystems, and the evidence for that isn't based on imagination. It's based on fossils, sediment layers, and chemical signals locked inside rocks and ice cores. Long before Megalodon, Antarctica had periods that were genuinely mild by modern standards, especially during the Cretaceous and early Cenozoic, when global climates were warmer. Antarctica was still positioned far south, but the planet's overall temperature and ocean circulation allowed high-latitude regions to support life that would seem impossible there today. There were forests, not just a few scraggly shrubs, actual forests, with trees that left behind fossilized wood, pollen and leaves. Some of these forests included species related to southern beech and other plants that can handle cool conditions, but still require a world that isn't sealed under permanent ice. This is one of the strangest things to imagine if you've only ever known Antarctica as a white blank. A forested Antarctica would have looked like a different planet, even though it was still Earth. The ground would have been dark, not white. The air would have smelled of soil, not just cold dryness. There would have been insects. There would have been birds. There would have been seasonal changes, but those seasons would have been about light and growth, not just survival against freezing. Now, by the time Megalodon arrived, Antarctica had already moved away from that greener era. The major shift toward large-scale glaciation began around 34 million years ago, near the boundary between the Eocene and Oligocene epochs. That's when Antarctica began developing significant ice sheets, and the world started cooling in a more permanent direction. But ice sheets don't appear like a curtain dropping at the end of a play. They grow, they retreat, they shift, they advance and pull back over millions of years, responding to atmospheric carbon dioxide, ocean circulation, and orbital patterns that change how sunlight hits the planet. So Antarctica during the Miocene, when Megalodon lived, was already a colder continent than it had been before, but it was not necessarily a fully sealed, unchanging ice kingdom. It was more like a place that had ice in the system, but still had flexibility. Some regions could have been heavily glaciated, others might have had seasonal melt and exposed coastal land. The ice margin could have moved. Sea levels could have risen and fallen with changes in global temperature and ice volume, and that creates a world that looks unfamiliar, even if it's not tropical. Let's imagine standing on the edge of Antarctica in that time. You're not standing on a wide, flat sheet of ice stretching forever inland. You're standing on a coastline that might include exposed rock, gravel, and steep slopes. In some places, glaciers would still reach the sea. In others, there could be more open shoreline. The ocean would lap against the land. Waves would break against stone. The water would be cold, but not necessarily filled with floating ice year-round. And inland, you might see ice fields in the distance, but they might not cover every visible surface. The landscape could look more like a rugged, cold coastal world than a pure frozen desert. It might remind you more of parts of modern Patagonia, southern Alaska, or the sub-Antarctic islands, depending on the region and the climate phase. Still harsh, still windy, still demanding, but not a place that feels entirely dead. One of the reasons Antarctica became the ice kingdom at all is because it became isolated. Today, Antarctica is surrounded by the Southern Ocean, and one of the most important features of that ocean is the Antarctic Circumpolar Current. It flows around the continent like a belt, separating Antarctic waters from warmer waters farther north. This current didn't exist forever. It strengthened as tectonic plates shifted and the ocean gateways opened up. When South America and Antarctica separated enough to open the Drake Passage, and when Australia moved away from Antarctica enough to open the Tasman Gateway, it allowed water to flow all the way around the continent. Once that flow became strong, Antarctica was effectively wrapped in a moving wall of cold water. Warm currents had a harder time reaching the continent. The climate cooled, ice could grow more easily and stay longer. But during Megalodon's era, this system was still in motion. The circumpolar current existed, but its strength and structure were still evolving over time. That means Antarctica's isolation wasn't necessarily as absolute as it is today. And that matters, because when a continent is less isolated, it can receive more warmth and moisture from the rest of the world. Moisture is important because ice sheets require snowfall. Ice doesn't grow just because it's cold. It grows because enough snow falls, accumulates, compresses into ice, and survives long enough to build thickness. So Antarctica's transformation depended on a balance. Cold enough for snow to stay, but also enough moisture to deliver snow in the first place. During certain periods, Antarctica could have been cold, but still receiving enough moisture to build glaciers. During warmer periods, the ice could retreat. During cooler periods, it could advance. This creates a continent that is not static. It's changing shape, and that shape change affects the ocean too. When ice sheets grow, they lock up water on land, lowering sea levels. When they shrink, sea levels rise. When sea levels rise, shallow seas expand. When shallow seas expand, marine habitats grow. When habitats grow, life spreads. So Antarctica before the Ice Kingdom wasn't just a land story, it was a sea story. Its changing ice affected coastlines and ocean productivity, and the ocean, in turn, affected climate through heat transport and carbon storage. Everything is connected. Now let's talk about what before the Ice Kingdom means in the Miocene context, because we don't want to accidentally picture Antarctica as fully green again. That older forested Antarctica was mostly earlier. By Megalodon's time, Antarctica was colder and more glaciated overall. But the Miocene had its own personality. The early to mid-Miocene included warmer intervals. Global temperatures rose, and Antarctic ice volume may have been reduced compared to later times. There may have been times when parts of Antarctica's ice sheets were smaller, more dynamic, and more vulnerable to retreat. That means there could have been more exposed coastal land, more open water, and potentially more accessible habitats for marine animals. It also means that the idea of Antarctica as a permanent ice kingdom, sealed and unchanging, doesn't fully apply. It was a continent that could still breathe a little. It could still shift. Now, one of the best ways to picture Antarctica in this transitional state is to imagine the ice not as a flat blanket, but as a living system. Glaciers are rivers of ice. They flow. They creep downhill under their own weight. They carve valleys. They grind rock into fine powder. They reshape the land slowly but relentlessly. In a Miocene Antarctica, glaciers would have been present, but their reach would have varied. Some would have extended far. Some would have pulled back. Some would have been stable for long periods, and others would have surged and retreated depending on conditions. If you were there, you might see massive ice tongues reaching toward the sea in some places, while other areas showed bare rock and sediment. You might see meltwater streams in warmer seasons, cutting channels through the ground, carrying gravel and mud toward the coast. You might see lakes forming near the edges of ice, temporary and cold, but still liquid. You might see cliffs where ice had once pressed against rock, leaving behind scars and polished surfaces. This is a land that has been worked over by ice, but not necessarily completely buried by it at every moment, and the ocean would carry the fingerprints of that ice. Meltwater changes salinity, it changes surface layers, it affects how water mixes, it can create stratification where lighter fresh water sits on top of heavier salt water, changing nutrient movement and oxygen levels. Sediment carried by glaciers and streams brings minerals into the sea. That can feed plankton blooms, that can feed krill-like organisms and small fish, that can feed larger fish, that can feed whales, and that brings us right back to why this matters for Megalodon. A productive ocean needs nutrients. Antarctica's shifting ice and changing coastline could have helped deliver those nutrients, especially in coastal zones where life thrives. So Antarctica before the Ice Kingdom wasn't empty, it was active. Even if the land was cold, the system was busy. Now let's address the question people often have in the background, even if they don't say it out loud. If Antarctica wasn't fully frozen, could you walk around comfortably? No. Even in warmer Miocene phases, Antarctica would still be a high-latitude place with harsh conditions. The light cycle would still be extreme. The winds would still be strong. The weather could still change quickly. It would still be isolated and difficult, but not comfortable is not the same as uninhabitable. Many environments on Earth are uncomfortable for humans, but full of life. Humans are not the measurement of whether a place works. We're just one animal with a narrow comfort range and a habit of complaining when it's slightly too hot or slightly too cold. Antarctica in the Miocene could support marine ecosystems that were rich and complex, even if the land was not inviting. And those marine ecosystems are the heart of this story, because the ocean doesn't care if the land is pleasant. The ocean cares about temperature gradients, nutrients, currents, and prey. If those things align, life flourishes. Now imagine the coastline again, but this time, imagine it as a map, not a modern satellite image. A living coastline that changes over time. Glaciers push forward and then retreat. Sea levels rise and fall. Shallow shelves appear and disappear. Bays open and close. This kind of coastline would create a shifting set of feeding grounds for whales and other marine mammals. Some years, certain areas might be accessible and rich. Other years, they might be blocked by ice or too cold. Animals would respond. They would adjust migration routes. They would follow food. Predators would follow them. That's how ecosystems work. Not by staying still, but by adapting. And when the world is in transition, adaptation becomes constant. This is also where the sense of before the Ice Kingdom becomes a feeling rather than a date. It's the feeling of a place that hasn't fully hardened into its modern identity. It's the feeling of a continent that still had open edges, still had movement between land and sea, still had seasonal breathing room. Now, if you're wondering what Antarctica sounded like in that era, it probably wasn't silent. We think of Antarctica as quiet because human presence is small and the landscape is often muffled by snow. But even modern Antarctica can be loud. Wind can roar, ice can crack like thunder, waves can smash against ice cliffs. Penguins can make a ridiculous amount of noise. In the Miocene, the soundscape would have included wind, surf, and animal life. Whales would have been a major presence. Their calls travel far underwater. The sea would carry those sounds through deep channels and along the continental shelf. Seals or seal-like animals could bark and grunt along shorelines. Birds would call overhead. And beneath all of it, the ocean would carry the constant background sound of moving water, currents rubbing layers against each other, and storms churning the surface. It would feel alive. And in that living sea, Megalodon would not be the only large creature. It would be part of a broad community of large animals, including whales that were evolving rapidly during this time. This matters because Megalodon wasn't a creature that existed in isolation. It was a product of its world. It was shaped by prey availability, competition, and environmental conditions. If Antarctica was still in a transitional state, still offering productive feeding grounds and open water in certain times and places, then it becomes easier to imagine Megalodon moving through southern waters as part of its broader range, not living there permanently like a resident with a mailing address, but appearing there when the conditions made sense. Now, as we move forward, the next thing to do is to connect this changing Antarctica to the ocean routes around it, because a continent doesn't just exist on its own. It shapes the water around it, and the water around it shapes everything that lives there. So the next step is to look at the Southern Ocean, not as a border, but as a highway, a moving, shifting system of currents and migration routes that could carry whales, fish, and potentially even Megalodon along the edges of Antarctica. Because once you understand that, the idea of a giant shark in the far south stops feeling like a strange rumour and starts feeling like part of a world that was simply built differently than ours. If you look at a map of Antarctica today, it's easy to think of it as a dead end, a giant white mass at the bottom of the world, a place you reach only if you mean to, a place you visit with careful planning, special ships, and a strong desire to wear layers. It doesn't feel like a crossroads, it feels like the edge of the page, but the ocean doesn't see it that way. The ocean doesn't have edges in the same sense. It has currents, temperature bands, shelves, and deep channels. It has paths that animals follow, not because they read maps, but because their bodies and instincts respond to food, water conditions, and seasonal rhythms. And when Megalodon was alive, the southern seas around Antarctica were not a quiet corner. They were part of a living network, a moving system that could connect continents, carry prey, and create feeding grounds large enough to attract giants. If you want to understand how a massive predator like Megalodon could have been part of the far south, it helps to picture the Southern Ocean as something like a highway. Not a straight road with signs and exits, but a shifting route system. A set of natural lanes formed by currents, temperature gradients, and migration patterns. Because Megalodon, like any large predator, would not have wandered randomly. It would have gone where the energy was, where prey was concentrated, where travel made sense, and the southern seas in the right conditions could offer exactly that. To begin, let's talk about what makes an ocean highway in the first place. It's not just water moving in a circle, it's a combination of forces that create predictable movement. Wind pushes the surface, Earth's rotation bends the flow. Temperature differences create density changes. Salinity affects how water layers stack. The shape of the seafloor funnels currents through certain regions. And once those currents exist, life starts to use them. Small organisms drift with them. Fish follow the smaller organisms. Larger animals follow the fish. And the biggest animals of all follow the entire system, like travellers who know where the busiest routes will be, even if they've never seen a map. In the modern world, one of the most important features of the Southern Ocean is the Antarctic circumpolar current. It circles Antarctica, moving huge volumes of water, and acting as a kind of barrier that separates cold southern waters from warmer northern waters. But during Megalodon's time, the ocean circulation around Antarctica was still developing. It wasn't a blank slate, but it wasn't necessarily identical to what we see today. The gateways between continents were opening and shifting. The strength of the circumpolar flow could have changed over time. The mixing between ocean basins could have been different. That means the routes available to marine animals could have been different too. And in a world where the climate was warmer in certain intervals, those routes could extend farther south than you'd expect. Now, imagine the Southern Ocean not as a wall of cold, but as a moving band of opportunity. In warmer phases, the boundary between temperate water and polar water could shift. The zones where whales feed could move. The distribution of fish could change. The edge of sea ice could retreat. This is important because predators like Megalodon would likely track these shifting zones. not because it was thinking about climate trends, but because it was responding to prey. Whales are one of the strongest reasons for any ocean highway to exist. Whales migrate. Even today, many whale species move between breeding grounds and feeding grounds. They travel thousands of kilometres. They follow seasonal cycles. They chase productivity. And whales don't migrate in a straight line like a commuter train. They move through corridors shaped by coastlines, currents, and water temperature. If the Miocene Southern Ocean supported whale populations moving along the edges of Antarctica, then those migration corridors would be like open lanes on the highway, and a predator that specialises in hunting whales would have a reason to patrol those lanes. It helps to picture Megalodon as a creature that didn't need to stay in one place. It could travel. Its size would allow long-distance movement with efficiency. Large animals often travel more efficiently than small ones, because they have more energy stored and can maintain momentum. Megalodon's body, like modern sharks, would have been built for steady cruising. Not necessarily constant speed, but endurance. The kind of movement that can carry an animal across large stretches of ocean without needing to stop for rest in the way land animals do. So the idea of Megalodon using the southern seas as a travel corridor isn't far-fetched. It's exactly what large marine predators do. Now, let's make this more specific. What routes would exist around Antarctica? There are a few major regions where the southern oceans connect to other parts of the world. Even today, the waters around Antarctica link to the Atlantic, the Pacific, and the Indian Ocean. In the Miocene, these connections were present, though the details of circulation patterns could differ. If you imagine an animal travelling south from South America, it could move along the continental shelf and then into the open southern waters. If it travelled from Africa or Australia, it could also move into southern latitudes, following prey and currents. The ocean is continuous, but animals tend to use certain paths more than others, because those paths are where food and favourable conditions line up. The continental shelf is one of the most important features here. A continental shelf is the shallow underwater edge of a continent. It's often a highly productive zone because sunlight can reach the bottom, nutrients can mix more easily, and ecosystems can build up in layers. Whales often feed along shelves because that's where prey is abundant. Fish, squid, and other organisms concentrate there, and predators often patrol shelves because shelves are predictable. Prey has fewer directions to escape. Depth changes create natural bottlenecks. The environment supports large bodies. So if Megalodon moved through southern waters, it likely spent time near continental shelves, including the Antarctic shelf, where feeding opportunities would be richest. Now, consider the way water moves along these shelves. Currents can run parallel to coastlines. Upwelling can bring cold, nutrient-rich water from depth to the surface. This fuels plankton blooms, which feed the entire food web. The Southern Ocean is known for being nutrient-rich. Even today, it has huge productivity in certain seasons, especially when sunlight returns after winter. In the Miocene, this productivity could have been strong as well, and in warmer phases it might have extended across wider areas of open water. So the southern seas could act like a feeding highway, not just a travel highway. This matters because a predator like Megalodon would not travel thousands of kilometres without feeding. It would move through zones where it could hunt along the way. It would not be a creature that needed a single home base. It could live along a route. Imagine a migration corridor where whales travel south to feed during a season of high productivity. They arrive in an area where plankton blooms support fish, squid, and other prey. The whales feed heavily, building energy reserves. Now imagine a predator that knows, in the way predators know, that this corridor produces opportunities. It doesn't need to hunt every day. It can wait, it can patrol, it can select moments, it can treat the corridor like a hunting ground stretched across the ocean. That's what a highway is in nature. Not a road you rush down, but a space where movement and feeding overlap. Now, one of the reasons the southern seas can feel so mysterious is because of their scale. The Southern Ocean is enormous. It wraps around Antarctica. It connects multiple basins. It includes deep trenches and wide shelves. It is not a small contained sea. It is a major part of Earth's ocean system, and because it is so open, it can support large animals that require space. Megalodon would have needed space. It would have needed room to move, room to hunt, and room to avoid competition. Competition is another important piece of this story. Megalodon wasn't the only predator in the Miocene ocean. There were other large sharks. There were early forms of predators that would later evolve into modern species. There were toothed whales, some of which were formidable hunters themselves. In fact, some extinct toothed whales like Leviathan are often compared to Megalodon in terms of their role as apex predators. Leviathan had massive teeth and likely hunted large prey as well. So the ocean was not empty, it was full of competition. In that kind of world, mobility is an advantage. If prey becomes scarce in one region, a mobile predator can move to another. If competition becomes intense, a predator can shift range. If seasonal conditions change, it can follow the best zones. So Megalodon's ability to travel would have been part of its success. And the southern seas, with their vast corridors and shifting productivity, could have been part of that travel system. Now let's talk about temperature lanes, because they matter more than people realise. In the ocean, temperature isn't uniform. Even in the same region, you can have layers. Surface water might be warmer, deeper water might be colder, currents can bring in different water masses. Animals often track these temperature boundaries. Some prey species prefer certain ranges, predators follow them. In the Miocene, with a warmer global climate at times, the temperature lanes that we associate with temperate zones could have extended farther south. That would allow animals that prefer milder conditions to travel closer to Antarctica. This doesn't mean they swam into near-freezing water without care. It means the boundary between too cold and acceptable could shift. If the boundary shifts, migration routes shift. And when migration routes shift, the ocean highway changes. So the southern seas as a highway is not a fixed road. It's a moving network that responds to climate. Now, imagine the view from above, as if you were a bird high in the sky, looking down at the ocean surface. You'd see long swells. You'd see patches of different colour where water masses meet. You'd see foam lines where currents converge. You'd see areas where the surface is smoother and areas where it's rougher, shaped by wind. These surface features are not just patterns. They often mark boundaries where nutrients gather and prey concentrates. In modern oceans, predators use these boundaries. Seabirds hunt along them, dolphins hunt along them, sharks hunt along them. Megalodon, if it existed in these waters, would have used them too. It would have been able to sense movement and chemical signals across distances. It would have followed the smell of blood, the scent of whales, the presence of feeding activity. It would have known where the ocean was busy. Now, let's imagine a specific scenario, not as a dramatic scene, but as a natural one. A pod of whales is moving south along a corridor near the Antarctic shelf. They are not rushing. They are travelling steadily. The water is cold but productive. The whales are following food. Below them, fish scatter and regroup. Smaller sharks patrol the edges. Seals or seal-like animals move in and out of the area. The whales begin to feed. They dive and surface. They release bubbles. They churn the water. Their presence creates a centre of activity. A large predator in the area senses this. It doesn't need to see it. It can detect it through vibration, scent and movement. It approaches from deeper water. It stays below the light. It moves slowly, conserving energy. It doesn't attack immediately. It watches. It waits. It chooses a target. Maybe a younger whale that lags behind. Maybe an injured whale. Maybe one that surfaces too far from the group. This is how predation often works. It's not a constant chase. It's timing. And because the southern seas are wide and open, the predator has room to approach without being noticed. That is what makes open ocean corridors so useful for large predators. There are fewer hiding places for prey, but there are also fewer obstacles for predators. Now, it's worth remembering that Megalodon's teeth suggest it was built for cutting through large bodies. Its bite force, estimated from models, would have been immense. It was likely capable of inflicting catastrophic damage quickly. In a hunting corridor, a predator like that doesn't need repeated attacks. It needs one effective strike. If it could disable a whale's tail or tear through a fin, it could turn a strong swimmer into a struggling animal. In cold water, struggling becomes even more dangerous. Energy drains faster, blood loss is more severe, the ocean takes over, so the highway becomes not just a travel route, but a place where predation can happen efficiently. Now, you might be wondering something else. If the southern seas were such a highway, why don't we find more Megalodon fossils in Antarctica? There are a few reasons. First, fossilization is rare. It requires the right conditions. Teeth are more likely to fossilize than cartilage, which is why we have teeth. But even teeth only fossilize if they settle in the right sediment and survive the pressures of time. Second, Antarctica is difficult to search. Much of it is covered in ice. Even coastal sediments can be hard to access. The fossil record there is incomplete, not because nothing happened, but because the evidence is buried or destroyed. Third, Megalodon's range may have been seasonal or limited. It may not have lived there constantly. It may have visited during warmer phases or followed prey temporarily. That would leave fewer fossils, so the absence of abundant fossil teeth in Antarctica doesn't mean the southern seas were irrelevant. It just means the record is patchy. And when you're talking about millions of years, patchy records are normal. Now, let's widen the view again. The southern seas weren't just a highway for Megalodon, they were a highway for life. Fish moved through them, whales moved through them, smaller predators moved through them, currents carried larvae and plankton across vast distances. Even drifting pieces of organic material could carry communities of small organisms. The ocean connects everything. So if you imagine Megalodon as a traveller, it fits into a system that was already built for movement. And that system would have been shaped by the same forces that shape it now, even if the details were different. Wind, currents, seasons, light, food. Now there's another factor that makes the southern seas feel like a highway, and it's one that people often forget. The southern oceans are not uniform in depth. There are deep basins where the water drops into darkness. There are shelves where it becomes shallow. There are ridges and underwater mountains that force water to rise and mix. This mixing creates hotspots of productivity. When water is forced upward, it brings nutrients from the deep. Those nutrients feed plankton. Plankton feed everything else. So the highway has rest stops in a way, places where life concentrates. In the Miocene, these hotspots could have been particularly important, because a warmer world doesn't always mean more nutrients everywhere. Sometimes warmer oceans can become more stratified, with less mixing. But the southern ocean has strong winds and currents that can keep mixing active. So even in warmer phases, the southern seas could remain productive. And productivity is what makes a corridor worth travelling. Now, imagine the difference between a highway through a desert and a highway through a landscape full of towns. The desert highway is long and empty. The other one has stops, resources and activity. The southern seas, especially near shelves and mixing zones, could have been the second kind. A corridor with repeated opportunities. That is exactly the kind of environment that supports large predators. Now, as we move forward, it helps to bring the picture closer to the land again. Because highways in the ocean don't just run through open water. They often follow coastlines. Coastlines provide structure. They guide movement. They create predictable routes. So the next thing to explore is what those coastlines actually looked like during Megalodon's time. How different were they from today? How much land was exposed? Where were the shallow shelves? Where were the bays and inlets? Because once you can picture the shape of the coast, you can picture how animals moved along it. And once you can picture movement, you can picture how a giant predator could use that movement to its advantage. Not by chasing everything in sight, but by letting the ocean bring opportunities to it, again and again, along the long southern route. When you look at Antarctica today, the coastline feels almost like a guarded secret. In many places, you don't see land meeting sea in the way you do on most continents. You see ice meeting sea, you see shelves of ice extending outward like frozen platforms, you see cliffs made of compacted snow and ancient layers pressed into a hard, pale wall. Even when rock is exposed, it often feels temporary, like the ice is only stepping aside for a moment before covering it again. That's the modern Antarctic coastline. It's dramatic, severe, and strangely clean. Not because it's simple, but because so much of it is hidden. But in the time of Megalodon, Antarctica's edges could have looked very different. Not everywhere, not all the time, and not in a way that turns it into some warm paradise. But different enough that if you were dropped into that era without warning, you might not immediately recognise the place you were standing. The coastlines were not just scenery. They were the meeting point between land and ocean, and that meeting point shaped everything. Where nutrients entered the sea, where animals gathered, where shallow shelves created feeding zones, where predators could patrol. If the southern seas were a highway, the coastlines were the lanes, the ramps, and the intersections. So let's slow down and build the picture carefully. Not as a fantasy map, but as a real coastline shaped by geology, climate, and time. First, it helps to understand what a coastline really is. A coastline is not a fixed line. It is a negotiation. It shifts when sea levels rise or fall. It changes when ice advances or retreats. It erodes under waves. It builds outward when rivers dump sediment. It gets carved by glaciers. It gets reshaped by storms. It is always being edited. Antarctica's coastline has been edited more aggressively than most. Because when you add large ice sheets into the equation, the coastline becomes a moving target. Ice presses down on the land. It grinds rock into fine powder. It scrapes valleys. It pushes sediment into the sea. It changes the shape of bays and shelves. Then it retreats and leaves behind a new outline. During Megalodon's time, Antarctica was already a continent with ice in the system, but it was still in transition. The ice was not necessarily as stable or as extensive as it is today. There were warmer intervals during the Miocene, and then cooler intervals as the world continued its long trend toward the colder conditions we know. That means Antarctica's coastline during this period could have been more exposed in some regions, more dynamic, and more varied. If you stood on the edge of the continent during a warmer phase, you might see rock and sediment that today would be buried. You might see a coastline that had more open water for longer parts of the year. You might see shorelines that were not blocked by massive ice shelves in the same way. The first big difference you'd notice is the presence of more visible land in some places. Modern Antarctica hides most of its land under ice. Even the highest peaks that poke out, called nunataks, are like small islands of rock in a sea of frozen surface. But in a period with less ice volume, more of the coastal margins could be exposed. That doesn't mean the interior was suddenly ice-free. The interior could still be heavily glaciated, but coastal exposure is often the first thing to change. Why? Because coastal areas are influenced by ocean temperature and seasonal melt. Ice near the edges can respond more quickly to climate shifts. If the ocean warms slightly, ice shelves thin. If air temperatures rise slightly, surface melting increases. If snowfall patterns change, ice flow changes, so the coastline becomes the flexible boundary. This flexibility matters because exposed coastlines create habitats that don't exist when everything is sealed under ice. They allow animals to haul out. They allow rivers and streams to deliver sediment. They create shallow bays where life concentrates. Now, let's talk about sea level, because sea level changes can reshape coastlines dramatically. During warmer phases, when global ice volume is lower, sea levels tend to be higher. More water is in the ocean rather than locked in ice sheets. Higher sea levels flood low-lying coastal areas, creating shallow seas, wider continental shelves, and more complex coastlines. During cooler phases, sea levels fall. Coastlines retreat outward. Land that was underwater becomes exposed. Shallow seas shrink. So Antarctica's coastline during Megalodon's time wasn't just a matter of ice, it was also a matter of water volume. If sea levels were higher in warmer intervals, the Antarctic shelf could have been broader in some places. Coastal basins could have been flooded. There could have been more shallow marine environments along the edges. Shallow marine environments are important because they are the nurseries and feeding grounds of the ocean. Many fish species use shallow areas to spawn. Many marine mammals feed along shelves. Many predators patrol these zones because prey is abundant and movement is more predictable. So a coastline with more shallow shelf area would be a coastline with more life. Now imagine the Antarctic shelf itself. Today, Antarctica has a continental shelf that is unusual in some ways. It is often deeper than many other continental shelves, partly because the weight of ice has depressed the land and because glacial processes have carved and shaped the shelf. In the Miocene, the shelf would still exist, but its exact shape and depth would vary depending on ice extent and sea level. If ice was less extensive at times, some shelf areas might have been less deeply carved. There could have been more gentle slopes, more areas where sunlight could reach the bottom. That would make coastal waters more productive, but even if the shelf was deep in places, productivity can still be high, because the Southern Ocean is driven by mixing and nutrient availability. So the coastlines weren't just about what you could stand on, they were about what the ocean could build around them. Now let's picture the physical look of the coast. A Miocene Antarctic coastline could include rocky headlands, cliffs shaped by wave action, beaches made of gravel and coarse sediment, muddy inlets where fine glacial flour settled, fjord-like valleys carved by glaciers, filling with seawater and creating deep bays. If you've ever seen modern glaciated coastlines in places like Norway, Alaska, or parts of Chile, you have a useful reference. Those coastlines have steep walls, deep water close to shore, and complex networks of inlets. Antarctica could have had similar features, especially in regions influenced by glacial carving. But the difference would be in how much ice filled those inlets. In the modern Antarctic world, many inlets and bays are occupied by glaciers and ice shelves. In the Miocene, especially in warmer intervals, some of these could have been more open. That would create sheltered marine environments. Sheltered bays matter because they provide calmer water. Calmer water allows different kinds of feeding and breeding behaviour. It allows marine mammals to rest. It allows fish populations to thrive. And sheltered bays can also become hunting grounds. Predators can use the structure of a bay to corner prey. Prey has fewer escape routes. The geography shapes movement. So a coastline with more open bays and inlets could have created a more complex hunting landscape. Now, consider sediment. Sediment is often overlooked, but it is one of the most important ingredients in coastal ecosystems. When glaciers grind rock, they produce fine sediment. When meltwater carries that sediment to the sea, it creates plumes of cloudy water. Those plumes carry minerals. Those minerals feed microscopic life. Plankton blooms can respond to nutrient input. Those blooms feed small animals. Those small animals feed larger ones. So the coastline is not just a boundary. It is a nutrient delivery system. In a Miocene Antarctica with seasonal melting in some regions, you could have meltwater streams delivering sediment during warmer months. You could have coastal waters turning slightly cloudy, with mineral-rich input. You could have bursts of productivity tied to seasonal changes. This is similar to what happens today in some glacial regions, where summer melt creates strong nutrient pulses. And those pulses attract animals. Fish gather where plankton blooms. Whales gather where fish gather. Predators gather where whales gather. So the shape of the coastline influences the entire food chain. Now think about ice at the edge. Even in warmer phases, Antarctica would still have ice. The coastline wouldn't be ice-free, it would be mixed. You might see glaciers reaching down to the sea in some places. You might see floating icebergs carving off and drifting away. You might see seasonal sea ice forming and melting. But the key difference is that the coastline might not be locked behind continuous massive ice shelves everywhere. Modern Antarctica has large ice shelves like the Ross Ice Shelf and the Filchner-Ronne Ice Shelf. These are enormous floating platforms of ice that extend far into the sea. In the Miocene, the extent of such shelves could have been smaller during warmer phases. They could have advanced and retreated. Their stability could have been different. A smaller ice shelf means more open water near the coast, more access for marine mammals, more sunlight penetration, and more more feeding opportunities, so even if ice was present, the coastline could be more open. Now, imagine walking along that coastline. The ground is uneven, rock underfoot, sometimes slick with moisture, sometimes rough and sharp. There are patches of sediment where meltwater has deposited fine material. The air smells of salt and cold stone. The wind is steady. It doesn't feel like a gentle breeze. It feels like the atmosphere is always moving down here, as if it has somewhere urgent to be. In the distance, you might see a glacier face, pale and towering, cracked with deep blue lines. You might hear the occasional thunder of ice breaking and falling into the sea. But you also see open water, dark water, moving with waves. You see foam lines. You see seabirds skimming the surface. And then far out you see a dark back rise and fall. A whale surfacing. Another blow. Another. That's the kind of coastline that feels alive. Not friendly, but active. Now, what about vegetation? By Megalodon's time, Antarctica was not covered in forest the way it had been much earlier. But during warmer intervals, it's possible that some coastal areas supported sparse vegetation, especially in ice-free patches. The evidence for this comes from fossil pollen, and plant remains found in certain Antarctic sediment deposits. We're not talking about lush green fields. We're talking about small hardy plants that could survive cool conditions, perhaps in sheltered microclimates. But even a small amount of vegetation changes the coastline. Plants stabilize soil. They influence how sediment moves. They create small habitats for insects and birds. They affect the chemistry of runoff into the sea. So if there were any patches of plant life, they would add complexity to the coastal environment. Now, let's think about the ocean just offshore. The waters near a continental shelf can be shallow for a long distance, depending on the shelf's width. In these shallow waters, sunlight can reach deeper. That supports algae growth. It supports fish populations. In deeper waters near steep shelves, the ocean drops quickly. That creates a different kind of environment, with deep channels close to shore. Antarctica likely had a mix of both, depending on the region. Some areas could have had broad shelves with gradual slopes. Others could have had steep drops and deep fjords. For Megalodon, both environments could be useful. Broad shelves are good for finding prey because prey concentrates there. Deep channels are good for ambush because predators can approach from darkness. So a coastline with varied shelf structure would be a coastline that supports different hunting strategies. Now imagine Megalodon using the coastline, not like a tourist following a scenic route, but like a predator using structure. It could patrol along the shelf edge where shallow water meets deep water. That boundary is often rich in life. Fish gather there. Marine mammals travel along it. It could move through deep channels using the darker water to stay hidden. It could approach feeding whales from below. It could also follow migration routes that hug the coast. Many marine animals use coastlines as guides. They follow the shape of land even when they can't see it, because the shelf and currents create predictable conditions, so the coastline becomes a travel guide. And the more complex the coastline, the more opportunities it creates. Now, let's talk about one of the most important features of Antarctic coastlines: icebergs. Even if the coastline was more open, glaciers would still carve icebergs into the sea. Icebergs drift, they melt, they carry sediment, they influence water temperature and salinity. Icebergs can create localized cold zones. They can also carry nutrients that stimulate plankton blooms as they melt. So in a Miocene Antarctic sea, icebergs could act like drifting nutrient sources. That's a strange thought, but it's real. Ice can feed life indirectly. A melting iceberg releases minerals into the water. That can stimulate phytoplankton growth. That can feed the food web. So even in a world that was warmer than today, ice would still play a role in supporting productivity. And productivity supports prey. Prey supports predators. Now imagine the coastline changing over time. In one period, a bay might be open water, rich with life. In another period, it might be filled with ice. In one phase, a shelf might be accessible for feeding whales. In another, sea ice might limit access. Animals would respond. Whales would adjust routes. Fish populations would shift. Predators would follow. So the coastline is not a fixed backdrop, it is part of the movement. And that movement is what makes the story of Megalodon and Antarctica feel possible. A static Antarctica, frozen solid for millions of years, would be harder to connect to a giant predator that likely preferred warmer waters. But a dynamic Antarctica, with shifting coastlines and changing conditions, could offer windows of opportunity. It could offer seasons when the water was productive and prey was present. It could offer corridors along shelves where travel and hunting made sense. It could offer sheltered bays where feeding concentrated. It could offer deep channels for ambush. So when you ask what the coastlines looked like back then, the most honest answer is this. They looked like a coastline in motion. Not ice everywhere, all the time. Not bare rock everywhere, all the time. But a shifting boundary between land and sea shaped by ice, water and climate. A coastline that could be rugged and exposed in one place, and glacial and sealed in another. A coastline that could change its outline over thousands of years, and sometimes even faster. And that kind of coastline is exactly the kind of environment that turns an ocean into a highway. Because when coastlines shift, currents shift. When currents shift, food shifts. When food shifts, animals shift. And somewhere in that shifting system, the largest shark to ever live could have followed the same rule that every predator follows. Go where the prey goes. Now, with the coastline in mind, we can step into the water itself. Because the next piece of this world is not just the shape of the land, but the character of the sea. What did the water feel like? How cold was it? How did it move? What did it look like under the surface? Because once you understand the water, you understand the stage Megalodon would have moved through quietly, steadily, and with a patience that only something enormous can afford. When people imagine prehistoric oceans, they often imagine them as bright and clear. Blue water, warm sunlight, and everything visible for miles like a postcard. The kind of sea where you could look down and see coral reefs, schools of fish, and a shark passing by in perfect cinematic lighting. But the southern waters around Antarctica, especially during the time Megalodon was alive, would have had a different personality. Even in warmer phases, this was not tropical water. It was not gentle water. It was not the kind of sea that feels inviting. It was a working ocean, a moving ocean, a place where the surface could look calm and the depths could still be restless. If you want to understand what it was like for Megalodon to move through the southern seas, you have to understand the water itself, not as a background, but as a living environment with its own rules. Temperature, colour, and movement sound like simple details, but they are the entire story. They decide which animals can live there. They decide where food gathers. They decide how far you can see. They decide how sound travels. They decide how a predator can approach and how prey can escape. So let's start with temperature. The Southern Ocean today is cold enough to feel like a warning. In many areas, the surface water stays near freezing. Salt water freezes at a lower temperature than fresh water, so you can have seawater below 0 degrees Celsius and still liquid. It's a strange fact that sounds like a trick, but it's real. During Megalodon's time, the southern seas were not always as cold as they are now. The planet went through warmer intervals, especially in parts of the Miocene. That doesn't mean the Southern Ocean became warm like a tropical lagoon, but it does mean the baseline conditions could shift. A few degrees warmer might not sound like much to a human, but in the ocean, a few degrees can change everything. It can change where sea ice forms. It can change how long open water lasts each year. It can change which fish can survive. It can change how much plankton grows and when. It can change migration routes. In the Miocene, the global climate was generally warmer than today in several stretches. Carbon dioxide levels were higher than modern pre-industrial times. Ocean circulation patterns were different. Antarctica was not as perfectly isolated by cold currents as it is now, because the system that wraps the continent in a ring of cold water was still evolving. So in some parts of the Miocene, the waters around Antarctica could have been less severe, especially in coastal areas and during warmer seasons. That would matter for Megalodon. because Megalodon was a large predator that likely depended on high-energy prey like whales. Whales would go where food is, and food depends heavily on water conditions. If the water was cold but productive, whales could still thrive. If the water was slightly warmer and still productive, whales could spread even more. And where whales go, large predators follow. Now, the next thing about temperature is that the ocean is layered. We often talk about the water temperature as if the ocean is one uniform bath. It isn't. Surface water can be warmer because it absorbs sunlight. Deeper water can be colder because it doesn't receive direct heat. Currents can bring in different water masses. Freshwater input from melting ice can create a lighter surface layer. So in the southern seas, you could have a surface layer that is relatively mild compared to modern Antarctic conditions, while deeper water remains cold and dark. That layering creates boundaries, and boundaries are where life concentrates. For example, when warm water sits on top of cold water, mixing can be limited. That can trap nutrients below the surface. But wind and storms can break that layering and bring nutrients upward, fueling plankton growth. The Southern Ocean is often windy. It's often stormy. That means mixing can be intense. Mixing keeps nutrients moving. Nutrients feed plankton. Plankton feeds everything else. So even if the water was cold, it could still be rich. That's an important point. Cold does not mean empty. In fact, some of the most productive waters on Earth are cold waters. Now let's talk about colour, because colour tells you what the water is made of. Tropical water often looks bright blue because it is relatively clear and because the light penetrates deeper. The water absorbs red wavelengths and reflects blue. In clear water, that blue looks vivid. But the southern seas, especially near Antarctica, would often look darker. They could be steel blue, grey blue, greenish, sometimes almost black under heavy clouds. The colour would change depending on light angle, cloud cover, and what was suspended in the water. If the water is rich in plankton, it can look green. If the water is full of sediment, it can look cloudy and grey. If the water is deep and the sky is overcast, it can look like a sheet of moving metal. During the Miocene, Antarctic coastal waters could have been influenced by sediment from glaciers and meltwater streams. Even if the coastline was more open, glaciers still existed. They still ground rock into fine powder. That powder, sometimes called glacial flour, can be carried into the sea. Glacial flour makes water look milky or cloudy in some cases. It can reduce visibility. It can change how sunlight penetrates. At the same time, nutrient input from sediment can fuel plankton blooms, which can turn the water green in seasonal pulses, so the water colour could shift through the year. In one season you might see dark, clear water with long swells. In another you might see greenish water filled with microscopic life. In another you might see cloudy water near the coast where meltwater enters. That variety matters because it changes visibility. Visibility is a big deal in predation. If the water is clear, prey can see threats sooner. If the water is cloudy, predators can get closer. Megalodon, like modern sharks, would not rely primarily on sight. Sharks have good vision, but they also have other senses that are more important for hunting. Smell, vibration detection, and electroreception allow them to find prey even in low visibility. So cloudy water could be an advantage for Megalodon. It could move in deeper water, approach from below, and remain unseen until the last moment. Now, colour also affects heat. Darker water absorbs more sunlight. If the surface water is darker because of plankton or sediment, it can absorb more heat, potentially influencing local temperature slightly. This is not a huge effect compared to global climate, but locally it can matter. So in a Miocene Antarctic coastal zone, patches of darker, productive water could warm slightly in sunlight, creating microzones that attract life. Now let's move to movement. The Southern Ocean is not still. It is one of the most dynamic ocean systems on Earth. It wraps around Antarctica, connecting the Atlantic, Pacific and Indian Oceans. It is driven by strong winds that circle the globe with little interruption. That means the water is always moving. There are surface currents, deep currents, eddies, and upwelling zones. There are places where water sinks and places where it rises. There are regions where different water masses collide and mix. Movement shapes everything. It shapes where plankton blooms occur. It shapes where fish gather. It shapes where whales feed. It shapes where predators patrol. If you were on the surface, you would feel that movement as long swells and constant wind-driven chop. The sea would rarely be flat. Even on calmer days, there would be a sense of motion, as if the ocean never fully rests. In storms, the movement would become violent. Waves would build into walls, spray would fill the air, the surface would become chaotic. But below the surface, the movement would feel different. In deeper water, waves fade. The surface chaos becomes a distant pressure pulse. Currents become the main motion. Water flows steadily, sometimes in powerful streams, sometimes in slow drifts. This is where Megalodon would have spent much of its time if it hunted large prey. A large predator can use deeper water as cover. It can approach from below. It can conserve energy by moving with currents, and currents can be used like conveyor belts. Modern marine animals often travel with currents to save energy. They position themselves in flow patterns that help them move efficiently. They also use eddies, rotating masses of water that can trap nutrients and prey. The Southern Ocean is full of eddies. These eddies can act like moving feeding zones. They concentrate plankton, they attract fish, they become hotspots. So in the Miocene, the southern seas could have been dotted with these moving hotspots, shifting with the currents, changing location over weeks and months. That would make the ocean feel like a living map. Not fixed points, but moving opportunities. Now, let's talk about sound and movement together, because in the ocean, sound travels far. Water carries sound better than air. A whale's call can travel for kilometres. The movement of a large animal can create low-frequency vibrations that spread through the water. Megalodon would likely be able to detect these vibrations. Sharks have sensory systems that allow them to feel pressure changes and movement. They can sense struggling prey from a distance. So in a moving ocean, Megalodon would not be hunting blind. It would be reading the water like a giant sensor field. The movement of currents would also carry scent. Blood in water spreads. Chemical signals spread. A predator can follow a gradient moving toward the source. In a strong current, scent trails can stretch far. They can also become complex, twisting and breaking apart in turbulent flow. That means the ocean is full of invisible information. For prey, that information can be dangerous. For predators, it is a guide. Now imagine how this plays out near Antarctica. A whale is feeding in a productive zone near the shelf. It dives and surfaces, churning the water. It releases waste, which adds nutrients. It stirs up prey. The whole area becomes active. Small fish gather. Seabirds circle above. The surface shows signs of feeding, splashes, foam, movement. Below, the water carries vibrations and scent. A large predator in the area senses this. It moves toward the activity. It uses the current to approach without wasting energy. It stays deep where it is darker and cooler. The prey might not notice until the predator is close, because the water is not clear like tropical water. It is darker. It is full of particles. The light is dimmer at high latitude. The surface might be rough, breaking up visibility. This environment favours ambush. Now, there's another important aspect of movement in the southern seas, and it's seasonal. Seasonal movement is not just about animals migrating, it's about the water itself changing. In polar regions, the return of sunlight in spring and summer can trigger huge blooms of phytoplankton. These blooms are the foundation of the food web. They feed small animals like krill-like organisms, which then feed fish, seals and whales. In winter, when sunlight is low or absent, surface productivity drops. Sea ice can form. The surface becomes less active biologically, so the southern seas have a pulse. In the Miocene, that pulse would still exist because Antarctica's position and light cycle were still polar, but the details of the pulse could change depending on temperature and ice extent. If the climate was warmer, the open water season could be longer, blooms could last longer, feeding seasons could be extended. That means the ocean highway could stay busy for longer stretches, more time for whales to feed, more time for predators to hunt. Now consider the movement of ice itself. Even in warmer phases, there would still be icebergs and seasonal sea ice. Ice moves with currents and wind. Ice can block certain routes and open others. Ice can create edges where life concentrates. Ice edges are often rich feeding zones because they concentrate nutrients and prey. Many animals feed along the edge of sea ice. So if Miocene Antarctica had seasonal sea ice, the ice edge could have been another moving lane on the highway. Whales might feed near it, seals might hunt near it, fish might gather under it, predators could patrol it. So the movement of ice would add another layer of structure to the water. Now, what about the feeling of the water itself if you could touch it? It would feel dense and heavy, cold enough to numb fingers quickly. Even if it was warmer than today, it would still be cold by human standards. It would have a sharpness to it. Saltwater cold is different from freshwater cold. It clings, it pulls heat out fast. The surface might feel slick with algae in some seasons. It might feel rough with waves. It might feel oily in calm conditions, reflecting the sky like a mirror. But the deeper you go, the more the world changes. Light fades, colours shift. Red disappears first, then orange, then yellow. Everything becomes blue-green and then grey. In productive waters, particles drift. Plankton glows faintly in some cases, if bioluminescent organisms are present. The water can feel full, not empty. And in that dim world, movement becomes more about pressure and vibration than sight. A large animal passing nearby would create a presence you could feel, even if you couldn't see it. That's the kind of water Megalodon would have known. Not clear and bright, not warm and gentle, but layered, moving, rich, and unpredictable. Now, it's worth remembering that this water was also shaping Antarctica itself. Water erodes coastlines, it deposits sediment, it carves channels, it interacts with ice. So the movement of the southern seas was part of the continent's transformation. Over millions of years, waves and currents would shape the edges of Antarctica, while glaciers carved from above. The coastline would be worked from both directions. That means the Miocene coastline was being sculpted constantly. And the water, with its temperature shifts, its changing colour, and its relentless movement, was the environment that connected everything. It connected plankton blooms to whale migrations. It connected whale migrations to predator patrols. It connected the changing climate to the changing coast. So when you picture the southern seas as Megalodon's environment, don't picture a flat blue surface with a shark fin cutting through it. Picture water that hides things. Water that moves like a system, not like a pond. Water that changes colour with life. Water that carries information. Water that can feel calm on top and dangerous underneath. Because in that kind of ocean, a giant predator doesn't need to announce itself. It can simply move with the current, deep and steady, letting the water do what it has always done, carry life where it needs to go. And as the southern seas carried life along the Antarctic edges, they also carried something else. They carried the sky above them, reflected in every wave, every swell, every shifting patch of colour. And to understand what Antarctica felt like during Megalodon's time, it helps to look up for a moment at the sky that hung over that ancient coastline, because it wasn't just cold air and clouds. It was part of the rhythm that shaped the entire world below. If you've ever seen footage of Antarctica, the sky is almost always part of the mood. It's not just background, it sets the tone. The light looks different, the clouds look heavier, the horizon feels wider than it should. Even when the weather is clear, the air has a sharpness that makes the sky look more intense, like someone turned up the contrast. And that's modern Antarctica, with its ice fields and its extreme cold shaping everything. But in the time of Megalodon, the sky above Antarctica would have been different in ways you might not expect. Not because it was always sunny or gentle, and not because the continent suddenly had tropical blue skies. It was still Antarctica. It was still far south. It still had long days and long nights. It still had winds that could make the world feel restless. But the sky would have belonged to a different climate system, a different balance of heat and moisture, a different stage of the planet's slow cooling. So if you stood on a Miocene Antarctic coastline and looked up, you would be seeing a sky that carried clues about everything below it. The ocean temperature, the storm patterns, the seasonal rhythm of light, and even the chances that something like Megalodon could pass through those waters at all. The first thing you would notice is the light. Antarctica's position near the pole means the sun behaves strangely, no matter what the climate is doing. That part doesn't change. The continent still experiences long stretches of daylight in summer and long stretches of darkness in winter. This is not a small detail. It shapes life and movement. In the summer, the sun can stay above the horizon for weeks or months, depending on where you are. It doesn't sit overhead like it does in the tropics. It circles low, moving around the sky in a wide loop, casting long shadows and giving everything a stretched out look. In winter, the opposite happens. The sun disappears. The world becomes dim or fully dark for long periods. Even when there is some twilight, it can feel like the day never fully arrives. So in the Miocene, even with warmer conditions, the light cycle would still feel extreme. You could have a summer coastline where the ocean glitters for hours without stopping. The same sunbeams sliding across the waves again and again as the sun circles. The sky never fully turning to night, just fading into a softer version of day. Then, later in the year, the same coastline could become a place of long darkness, where the sea is harder to read, and the wind sounds louder because there's less light to distract you from it. That kind of light cycle changes how animals behave. Many marine animals time feeding to light availability. Plankton blooms depend on sunlight. Fish follow plankton. Whales follow fish. Predators follow whales. So the sky's behaviour, the long daylight and long darkness, is directly tied to how the southern seas become busy or quiet. Now the second thing you would notice is the angle of the sun. In high latitudes, sunlight arrives at a lower angle. It travels through more atmosphere. That can change the colour of the light. It can make it softer and more golden at times, even during midday. It can also make shadows longer. It can make the surface of the ocean look like a sheet of moving metal, because low-angle light reflects more strongly. In a world with less ice at the coast in some phases, you might see darker land surfaces absorbing more sunlight. Rock absorbs heat more than ice does. Dark water absorbs more heat than ice does. That can influence local conditions slightly, especially during long summer daylight. So the sky's light doesn't just illuminate, it participates. Now, let's talk about clouds, because clouds are the personality of the sky. Modern Antarctica often has a sky that feels heavy and fast-changing. Storm systems roll through. Clouds form in layers. Fog can appear suddenly and erase the horizon. The weather can shift from calm to chaotic in a short time. In the Miocene, the sky would still have been active, but the balance of moisture could have been different. A warmer world tends to hold more water vapour. Warm air can carry more moisture than cold air. That means a warmer Miocene climate could have supported more cloud formation in some regions, more precipitation, and more frequent storms, depending on circulation patterns. So the sky above a different Antarctica might have been busier with cloud activity than you'd imagine. It might not have been the clear, dry polar sky you sometimes see in modern footage. It could have been more humid, more layered, more prone to fog and low cloud cover near the coast. Fog is worth mentioning, because fog changes everything about how a place feels. Fog makes distances uncertain. It makes the ocean look closer than it is. It makes the sky feel lower. It muffles sound slightly, but it also makes every nearby sound sharper. If you stood on a Miocene Antarctic coastline with fog rolling in, You might see the sea fade into grey within a few hundred metres. You might hear waves but not see them clearly. You might catch the shadow of a whale surfacing, then lose it again. Fog also affects predators and prey. Low visibility can make hunting easier for animals that rely on senses other than sight. A large shark doesn't need a clear view. It needs movement, scent, and vibration. So a foggy, cloud-covered southern sea could be a place where Megalodon could move without being noticed from above. Now, storms. The Southern Ocean is famous for storms because of the winds that circle the globe in the southern latitudes. There is less land to interrupt the flow. Winds can build strength over long distances. Storm systems can move quickly and grow large. That would have been true in the Miocene as well, because the basic geography of the Southern Ocean still allowed for powerful wind patterns. But a warmer world can shift storm behaviour. Storm tracks can move. The intensity and frequency can change. The amount of precipitation can increase. So a Miocene Antarctica might have had periods of heavy storms that brought rain or wet snow to coastal areas, depending on temperature. In warmer seasons, precipitation might fall as rain in some regions, something that feels almost unthinkable in modern Antarctica. Rain in Antarctica is not a common modern experience, but in a warmer climate it becomes more possible. Rain changes coastlines. It increases runoff. It feeds rivers and streams. It carries sediment into the sea. It affects nutrient delivery. So the sky, through rain and storms, could directly influence coastal productivity. And again, productivity is the key. A productive sea supports whales. Whales support large predators. Now let's talk about wind, because wind is constant in Antarctica. Even in a warmer phase, the continent's position and the surrounding ocean would still create strong winds. The temperature difference between the interior and the coast can drive winds. The movement of storm systems drives winds. The shape of the land and ice influences wind direction and speed. In modern Antarctica, katabatic winds are famous. These are cold, dense winds that flow downhill from the interior, accelerating as they descend. In the Miocene, katabatic winds could still exist, especially in colder seasons, because even if the climate was warmer overall, the interior could still be cold and elevated. Cold air would still sink and flow. But if the ice sheets were smaller or less extensive at times, the wind patterns could change. Less ice changes surface roughness. It changes how air flows. It changes local temperature gradients. So the wind above a different Antarctica could have felt slightly different in some places. Still strong, still persistent, but not necessarily identical. Wind shapes the sea surface. It creates waves. It creates foam lines. It drives mixing. Mixing brings nutrients up. Nutrients feed plankton. Plankton feeds the food web. So wind is another link in the chain. Now, the sky above a different Antarctica would also have looked different because of the absence or reduction of the modern ice glare in some regions. Ice reflects light strongly. It makes the landscape bright. It can make the sky feel whiter because light bounces off the surface and fills the air. If there was more exposed rock and darker coastal land, the overall brightness would be reduced. The contrast would be different. You might see a coastline that feels darker, more grounded, less blinding. The sky could look deeper in colour because less light is bouncing back upward. This is a subtle difference, but it changes the mood. Now imagine standing there during a long summer day. The sun circles low, the ocean surface glints, the wind keeps moving, clouds form and break apart. In the distance you might see a line of mist where colder air meets warmer water. The light never fully fades, but it softens. The world feels stretched out. Time feels strange because the sky refuses to give you a clear signal that the day is ending. This matters for animals too. In long daylight, feeding can continue for extended periods. Plankton can grow for longer hours. Fish can feed longer. Whales can feed longer. A feeding season with extended daylight can be intense. It can create a short window where animals pack on energy quickly, because the environment provides a burst of resources. and where resources concentrate, predators appear. Now imagine the winter. The sky becomes darker, the sun disappears. The ocean surface is harder to read. The wind feels colder because the light is gone. Sea ice might form more extensively. The world becomes quieter in some ways, but not silent. Whales might migrate away. Some animals remain. Others follow the ice edge. Predators adjust. If Megalodon ever moved into these southern waters, it likely did so when conditions were favourable, when prey was present, and when the sea offered open corridors. So the sky's seasonal rhythm would have shaped when the southern seas were part of Megalodon's world. Now, let's consider the sky at night, because even in a warmer Miocene Antarctica, nights would be something special. In winter, the night can last for weeks. The stars would be sharp in clear conditions, because cold air can be very dry and stable. But in a warmer, more humid coastal climate, you might have more cloud cover, more fog, and fewer clear nights. Still, when the sky did clear, it would be wide and deep, and the absence of human light would make it overwhelming. The Milky Way would stretch across the sky, the stars would feel close. The horizon would be a dark line between sea and sky. If auroras occurred, they would add movement to the darkness, curtains of light shifting and rippling, reflecting faintly on the ocean surface. Auroras are driven by solar particles interacting with Earth's magnetic field, so they are not dependent on climate. They could have been present then as they are now, so even in a different Antarctica, the aurora could still paint the sky. Now imagine that view paired with the ocean below, a dark sea moving steadily, the sound of waves, the occasional distant crack of ice, the slow, steady breathing of a whale surfacing in the dark, and somewhere beneath the surface, something large moving through the water, unseen, guided by senses that do not need light. That's the kind of scene that makes Antarctica feel less like a frozen blank and more like a living world. Now it's worth remembering that the sky also carries temperature signals. If the sky's cloudy, it traps heat. Clouds act like a blanket, slowing the loss of heat from the surface at night. That can keep coastal areas slightly warmer. If the sky is clear, heat escapes more easily. Nights become colder. Ice forms more readily. So cloud patterns influence local climate. In a Miocene Antarctica with different greenhouse gas levels and different ocean circulation, cloud behaviour could be different. That could affect how long open water lasts. It could affect how often sea ice forms. It could affect the length of the feeding season. So again, the sky is not separate from the ocean. It's part of the same system. Now, think about what the sky would have looked like during storms. The horizon would disappear. The clouds would lower. The wind would roar. The sea would become chaotic. Spray would fill the air. In that kind of weather, surface hunting becomes difficult. Visibility is low. Waves are dangerous. But underwater, below the surface chaos, conditions can be calmer. A large predator can use storms as cover. Prey can become disoriented. Sound becomes messy. Movement becomes harder to predict. So storms could be hunting opportunities. This is one of the strange truths of nature. What looks like danger to us can look like advantage to a predator. Now, as we keep building this world, the sky above a different Antarctica gives us one more important clue. It reminds us that Antarctica is not only cold, it is seasonal, it is rhythmic. It is shaped by light and darkness as much as by temperature. And that rhythm shapes everything below. So when you imagine Megalodon alive in the same world as Antarctica's transformation, don't imagine a static scene. Imagine a coastline under long daylight, then under long darkness. Imagine an ocean that blooms with life in one season and tightens in another. Imagine whales arriving and leaving following the sky's rhythm. Imagine predators responding, not to the calendar, but to the movement of prey and the pulse of the sea. Now, with the sky in mind, we can look down again toward the land itself. Because Antarctica wasn't just rock and ice. Even in a colder world, There were places where life could cling on land in sheltered pockets, in rare moments of exposure. And understanding what grew there, what survived there, helps us understand how different this Antarctica really was, even while Megalodon was still moving through the oceans of the same planet. When you hear Antarctica, the idea of a forest feels almost like a mistake. It sounds like someone mixed up continents, like someone meant to say Amazon and accidentally said Antarctica instead. Because modern Antarctica does not give you even the smallest hint of trees, it gives you ice, rock, and the occasional stubborn patch of moss that looks like it's holding on out of pure spite. So when we talk about forests and green pockets of land in Antarctica, especially during the time Megalodon was alive, we have to be careful about what we mean. We're not talking about a continent covered in lush woodland during the Miocene the way it may have been in much earlier ages. Antarctica's truly forested era was largely before the major ice sheets became established, when the planet was warmer overall and Antarctica had not yet become the cold, isolated continent we know. But not a forested continent is not the same as a continent with no green at all. Antarctica during Megalodon's time was a place in transition. It had ice in the system, but it wasn't fully locked into the modern ice kingdom. That means there could have been stretches, especially in warmer intervals and in certain coastal regions, where land was exposed for long enough to support plant life. Not tall trees waving in the wind, not thick jungle, but plants, green pockets, small ecosystems clinging to exposed ground, especially in sheltered areas. And even small plant life matters. It changes the land. It changes runoff. It changes sediment movement. It changes nutrient input into the sea. It changes the entire feeling of the coastline. So let's slow down and look at what Antarctica could offer above the waterline during the Miocene, when Megalodon was alive somewhere in the oceans. The first thing to understand is that Antarctica's green is not one thing. It is not a single landscape. It is a collection of possibilities shaped by temperature, light, moisture, and exposure. A plant doesn't care about the name of the continent. It cares about conditions. It needs enough liquid water, at least seasonally. It needs some kind of substrate to anchor to, soil, sediment, rock cracks. It needs light, which Antarctica has plenty of in summer. It needs temperatures that don't kill it outright. In the modern world, Antarctica is so cold and so ice-covered that plants are extremely limited. But even now, life finds a way. There are mosses, lichens, algae, and a small number of flowering plants in the Antarctic Peninsula region. That's modern Antarctica, in its coldest identity. So if the Miocene climate was milder in certain intervals, it becomes easier to imagine more extensive plant life in exposed coastal areas. Not widespread, not continuous, but present. Now, when people hear forests, they often think of the older Antarctic story, the one that belongs to a warmer Earth. Antarctica once had forests in deep time. Fossil evidence shows that it supported tree growth in the past, including species related to southern beech and other plants that can tolerate cooler conditions, but still require a world that isn't frozen solid. These forests existed during periods when the global climate was warmer and Antarctica's ice sheets were not established the way they are now. By the Miocene, Antarctica had already cooled significantly compared to that era, but it had not become instantly and uniformly frozen. The Miocene had warmer intervals, and those intervals could have allowed certain coastal regions to support more plant life than the modern continent. So instead of imagining a continuous forest, imagine green pockets. Imagine sheltered valleys near the coast where ice retreats seasonally. Imagine rocky slopes that face the sun, warming slightly during long summer daylight. Imagine areas where meltwater trickles through sediment, creating damp ground for a few months. These are the kinds of places where plants could exist. And in Antarctica, microclimates matter. A microclimate is a small area where conditions differ from the surrounding region. It could be warmer because it's sheltered from wind. It could hold moisture longer because it sits in a depression. It could receive more sunlight because of slope angle. In a harsh environment, microclimates are everything. They create survival zones. So in Miocene Antarctica, even if the overall climate was cold, microclimates could allow plant life in certain places. Now, what kinds of plants are we talking about? We're not dealing with palm trees or tropical vines. We're dealing with hardy plants adapted to cool temperatures and strong seasonal changes. Mosses are a likely candidate. Mosses don't need deep soil. They can grow on thin substrates. They can hold moisture. They can survive cold and dryness by going dormant and reactivating when conditions improve. Lichens are another. Lichens are not a single organism, but a partnership between fungi and algae or cyanobacteria. They are incredibly tough. They can grow on bare rock. They can survive extreme cold and intense sunlight. Algae would also be present, especially in wet areas and in meltwater pools. Algae can form green films on rocks and soil. They can bloom in water. They can even exist within snow and ice. If there were any small flowering plants in certain regions, they would likely be simple, hardy species, similar to what exists in modern Antarctic fringe areas. But even without flowering plants, mosses and lichens alone can create a visible green presence. Now, why does this matter for the story of Megalodon? Because the land affects the sea. Plant life influences runoff. It influences how sediment moves. It influences nutrient delivery. If you have exposed land with plant cover, even sparse, you have organic material entering the coastal waters. You have soil formation, even thin soil. You have more stable sediment. When rain falls or snow melts, water carries organic matter and minerals into the sea. That can feed coastal plankton blooms, and plankton blooms are the base of the food web, so green pockets on land can support life in the sea indirectly. Now imagine the coastline during a Miocene summer. The sun stays up for long hours. The air is cold but not unbearable in every moment. Meltwater runs in small streams. It pools in shallow depressions. On rocky surfaces, mosses and lichens cling in patches. The green is not bright like a meadow. It's darker, muted, almost hidden until you look closely. But it's there. In sheltered areas, you might see low shrubs or hardy plants in rare pockets, depending on the region and the exact climate phase. The land is not dead. It's quiet, but alive, and this quiet land feeds the sea. Meltwater carries fine sediment and minerals. It creates plumes in coastal water. Those plumes can stimulate productivity. In the sea, phytoplankton blooms respond to light and nutrients. They turn the water greenish. They feed small animals. Small animals feed fish. Fish feed seals and whales. Whales attract predators. So the land, even with sparse plant life, is part of the chain. Now let's talk about the idea of strange plants, because the Miocene world was not the modern world. Plant communities were different. Some plant lineages that existed then are gone now. Some were more widespread. Some were still evolving into their modern forms. Antarctica's plant life, even in small pockets, could include species that would feel unfamiliar if you could see them. Not necessarily because they were alien, but because ecosystems shift over millions of years. Species come and go, climate changes, continents drift, isolation increases. So a Miocene Antarctic plant patch might include combinations that no longer exist together today. It might include hardy shrubs or low-growing plants adapted to long daylight and cold seasons, perhaps related to southern hemisphere lineages that once had a broader range. It might include fungi and microbial mats that thrive in wet, cold conditions. It might include algae communities that bloom in meltwater pools, leaving bright green stains on rock. The overall impression would be subtle, not lush, but subtle is still meaningful. Now let's picture what it would feel like to walk into one of these green pockets. You're in a sheltered valley near the coast. The wind is reduced because rock walls block it. The air feels slightly warmer, not warm but less biting. The ground is damp in places with meltwater seeping through sediment. There are patches of dark green moss clinging to rock and soil. There are lichens, pale and crusty, spreading across stone like slow paint. The smell is faint but real. Wet earth, minerals, salt in the air. If you touch the moss, it feels soft and cold. It holds water like a sponge. It is alive, but it moves at a pace that matches the environment. Above you, the sky is pale. The sun is low but constant. In the distance, you can hear the ocean. Waves breaking. The occasional crack of ice. The call of birds. This is not a place of abundance, but it is a place of persistence. Now think about what these green pockets mean for animals on land. Antarctica during the Miocene was not full of large land animals. By this time, the continent was already isolated and cooling. But small life could still exist. Insects, for example, can survive in harsh environments. Birds could visit coastal areas. Even if land animal diversity was limited, the presence of plant life would support microbial communities, small invertebrates and birds. And birds matter because they connect land and sea. Birds feed in the ocean and rest on land. They bring nutrients in the form of waste. They transport seeds and spores. They shape small ecosystems, so even a sparse green pocket could be influenced by bird activity. Now, the idea of Antarctica having any green at all during Megalodon's time also reminds us of something important. Antarctica was not always the same level of cold. The Miocene was a time of fluctuation. There were warmer phases and cooler phases. Ice advanced and retreated. Sea levels changed. So these green pockets might not have been permanent. They could appear in warmer intervals and shrink in cooler ones. That means the land itself could have a seasonal and long-term pulse. In warmer phases, more land exposed, more plant life, more runoff, more coastal productivity. In cooler phases, less land exposed, less plant life, more ice, different productivity patterns. This pulse would influence the sea, and the sea would influence where whales feed, and whales would influence where predators hunt. So again, the land and sea are linked. Now, it's worth thinking about how strange it is that Antarctica's plant life story is still partly hidden from us. Much of Antarctica's past is buried under ice. Fossils are hard to access. Sediment records are incomplete. We know pieces. We have clues. We have pollen grains preserved in rock layers. We have fossil wood from older periods. We have chemical signals that hint at temperature and vegetation. But the full picture is still being assembled. That means Antarctica's Miocene green pockets are not fully mapped in our minds yet. We can describe the conditions that would allow them, and we can point to evidence that plant life existed in certain times and places, but we cannot draw a perfect photograph of it. Still, we can build a realistic impression. A coastline with exposed land in places, a climate that allows seasonal melt, patches of moss and lichen, occasional low vegetation in sheltered spots, microbial mats in wet areas, a landscape that is mostly rock and ice but not entirely, and in that landscape the ocean is always nearby. The ocean is the main source of life energy in this region, so the green pockets on land would be small, but the life in the sea could be huge. That contrast is part of what makes Antarctica such an unusual place, both now and then. On land, life clings. In the sea, life can explode. Now let's bring this back to Megalodon again, because it's easy to drift too far into the land story. Megalodon didn't care about moss, it didn't care about lichens, it didn't care about small green patches, but it cared about the ocean that those patches helped feed. If coastal productivity was boosted by runoff and sediment input, it would support fish and marine mammals. If marine mammals were abundant, it could support large predators. So the presence of any land-based green pockets is another sign that the Antarctic coastal environment could be more complex and productive during certain Miocene intervals than the modern image suggests. It's another piece of evidence that Antarctica was not yet the fully sealed ice kingdom. Now, imagine looking out from one of these green pockets toward the sea. The land behind you is rocky, with patches of damp moss. The air is cold, but the sun is present. In front of you, the ocean stretches out, dark water moving steadily. In the distance, a whale surfaces, a burst of mist, then another. The sea is full of movement you can't see. Currents sliding beneath the surface, fish moving in schools, predators moving in silence, and somewhere out there, beyond the reach of your eyes, something enormous could be cruising along the shelf edge, using the southern seas as a route, not because it belongs to Antarctica, but because Antarctica, in that moment, is offering the ocean what it always offers when conditions align: food. Now, as we continue, we need to step fully into the water again, because the land is only the edge of the story. The real world of Megalodon and Antarctica is the marine world, the creatures that lived there, the prey that drew predators in, the communities that fill the southern seas. So next, we're going to meet the animals of those Antarctic waters, the ones that would have shared the sea with whales, and the ones that would have lived in the same world where a giant shark could pass through like a shadow, moving with the currents, never needing to announce itself. When people think about Antarctica's wildlife, they usually think about the modern cast. Penguins in groups waddling and diving like they own the place, seals stretched out on the ice like they're taking the world's coldest nap, whales surfacing in dark water, their breath hanging in the air like smoke, krill swarming in numbers that are almost hard to believe. It's a powerful image, and it's not wrong. Modern Antarctica is full of life, even though the land looks empty. The sea is where everything happens. But in the time when Megalodon was alive, the Antarctic waters had a different community. Not empty, not quiet, just different. Some familiar ideas were there, like whales, fish, and marine predators. But the exact species were not the ones we know now. Many modern Antarctic animals either didn't exist yet, or they were still evolving into their modern forms. Some extinct animals were present, and they would look strange to us, not because they were mythical, but because time changes everything. If you want to picture the creatures of the Antarctic waters during Megalodon's era, you have to picture an ocean that is both recognizable and unfamiliar. The rules of the sea were the same. The food web was still built from tiny life upward. But the faces in that web had changed, and those creatures matter, because Megalodon didn't live in isolation. It lived in an ecosystem. It needed prey, it faced competition. It moved through a world where other animals were hunting, feeding, migrating, and surviving. So let's step into those waters and meet the inhabitants, starting from the smallest level, because the smallest level is always where the real story begins. At the base of the Antarctic marine ecosystem, then as now, would be microscopic life. Phytoplankton, tiny photosynthetic organisms floating near the surface, turning sunlight into energy. They're easy to overlook because they're too small to see as individuals, but together they can change the colour of the ocean. They can make the water look greenish or cloudy. They can create blooms that stretch for kilometres. In the Miocene, phytoplankton would have been just as important. The species composition could differ, but the function would be the same. When sunlight returns in spring and summer, phytoplankton grows rapidly. It feeds the next level of the food web. That next level includes small drifting animals, zooplankton. Today, the most famous Antarctic zooplankton is krill, because krill is the foundation of so much modern Antarctic life. In the Miocene, there would have been krill-like organisms and other zooplankton species filling similar roles. These small animals feed on phytoplankton. They convert microscopic energy into something larger animals can eat. And that's where the ocean starts to feel crowded. Because once you have abundant plankton, you get fish. The fish of the Miocene southern seas would include a mix of species, some extinct, some early relatives of modern groups. Fish are the middle of the food web. They eat plankton and smaller animals, and they are eaten by bigger predators. In cold and productive waters, fish populations can be dense. They can form schools that move like living clouds. They can fill coastal zones, shelf edges, and deeper channels. Some fish would have lived near the bottom. Others would have lived in open water. Some would have been small and fast. Others would have been larger and slower. And fish would not be alone. Squid and other cephalopods would also be present. Squid are important prey for many marine animals, including whales, seals, and large fish. They can live in deep water and come up to feed at night. They can move quickly and change colour. They are both predators and prey. So in Miocene Antarctic waters, squid would add another layer of movement. Now once you have fish and squid, you get medium-sized predators. Smaller sharks would have been present. Not all sharks are giants. Many are modest-sized, fast and adaptable. They hunt fish and squid. They patrol shelf edges. They move through different temperature zones. There would also be large bony fish predators, perhaps similar in role to modern predatory fish like tuna or other fast hunters, though the exact species would differ. And then above them you have marine mammals. This is where the Miocene ocean becomes especially important. The Miocene was a time of whale evolution and expansion. Many whale groups diversified. Some whales were becoming larger. Some were developing feeding strategies that would later define modern baleen whales. Toothed whales were also present, and some were formidable predators. In Antarctic waters, whales would have been major players. Some would be baleen whales or early relatives, filtering small prey from the water. Others would be toothed whales hunting fish and squid, and in some cases hunting other marine mammals. This matters because whales are not just prey for Megalodon. They are ecosystem engineers. Whales stir the water when they feed. They bring nutrients to the surface when they dive deep and then release waste near the surface. They create feeding opportunities for birds and fish. A whale-rich ocean is a busy ocean. So in the Miocene southern seas, whales would likely be among the most important animals shaping the ecosystem. Now what about seals? Modern Antarctica has seals that are well adapted to cold water and ice. In the Miocene, seals and seal-like animals were evolving and spreading. Some early pinnipeds were already present in the southern hemisphere. Seals are important because they are both predators and prey. They hunt fish and squid. They compete with other predators. They also become targets for larger predators. So if seal populations existed in Miocene Antarctic waters, they would add another layer to the food web. And then there are birds. Modern Antarctic birds include penguins, petrels, skuas, and other seabirds. Penguins are especially iconic. In the Miocene, penguins already existed. In fact, penguins have a deep evolutionary history, and some ancient penguin species were larger than modern ones. By the Miocene, penguins were already established as marine birds, diving and feeding in cold waters. The species would differ from modern penguins, but the lifestyle would be recognizable. So you could imagine penguin-like birds diving in the coastal waters, chasing fish, surfacing with quick breaths, then disappearing again. Seabirds would also be present, feeding on fish and scavenging. Birds connect the surface world to the underwater world. They respond quickly to prey concentrations. Where fish gather, birds gather. So birds would be part of the visible activity in the Miocene southern seas. Now, with all of these animals present, we can talk about the giants. The whales were giants. But they were not the only large animals. There were likely large predatory whales as well, depending on the region and time. Some extinct toothed whales had massive teeth and could hunt large prey. This creates an interesting dynamic. Megalodon is often imagined as the unstoppable apex predator, but it lived in an ocean with other powerful hunters. So if Megalodon entered Antarctic waters, it would not be the only danger. It would be one of the dangers. Competition could shape where it hunted and how it behaved. If large predatory whales were present, they could compete for prey. They could target similar animals. They could even pose a threat to young sharks. So Megalodon's relationship with the Antarctic ecosystem would involve not just hunting, but navigating competition. Now, let's focus on the prey that would matter most to Megalodon. Large whales. In the Miocene, baleen whales were diversifying. Some were becoming more specialised in filter feeding. This could create large populations of whales feeding on small prey in productive waters. These whales would be the perfect prey base for a large shark. Why? Because filter-feeding whales often gather in feeding grounds where prey is abundant. They can be predictable. They can spend time in one area feeding, rather than constantly moving at high speed. A predator can exploit that. A large shark can patrol the edges of a feeding ground, waiting for a vulnerable individual. A young whale, a sick whale, a whale separated from the group. The Miocene was also a time when whale sizes were changing. Some whales were smaller than modern giants. Some were intermediate. Some were growing larger. Even a smaller whale is a massive amount of food for a predator. So Megalodon's presence in an ocean with abundant whales makes sense. Now what about other large animals? There would likely be large fish and other marine reptiles. By the Miocene, the age of giant marine reptiles like plesiosaurs and mosasaurs was long gone. Those animals disappeared at the end of the Cretaceous, millions of years before Megalodon. So the Miocene ocean did not have those classic dinosaur-era sea monsters. Instead, it had mammals and sharks dominating the top levels of the food web. That's an important shift. The Miocene ocean is not a reptile ocean. It's a mammal and shark ocean, and that makes the Antarctic waters of that time feel closer to our world, even if the species are different. Now, imagine the Antarctic sea surface during a productive season. The water is dark, but it has a greenish tint in places where plankton is thick. The wind pushes waves into long lines. Birds circle and dive. Fish schools move near the surface, flashing briefly when they turn. Squid rise and fall in deeper layers. Whales surface in slow rhythms. Their blows hang in the cold air. Seals or seal-like animals move through the water, quick and agile, hunting fish. Smaller sharks patrol the edges, drawn by the activity. This is a full ecosystem. Now, where does Megalodon fit into this? It fits at the top, but it doesn't replace everything else. It sits above it. It would likely ignore small prey most of the time. It would focus on large targets, but even a top predator is influenced by the lower levels. If plankton blooms are strong, fish populations rise. If fish populations rise, marine mammals thrive. If marine mammals thrive, Megalodon thrives. So Megalodon's presence depends on the health of the whole system. Now, let's think about how these creatures interacted with the Antarctic environment. The Antarctic waters were cold, but productive. That means animals needed adaptations. Whales have blubber. Blubber is insulation and energy storage. It allows whales to feed in cold waters without losing too much heat. Seals also have blubber and thick fur, depending on species. They are built for cold water hunting. Fish in cold waters often have special adaptations. Some modern Antarctic fish have antifreeze proteins that prevent their blood from freezing. In the Miocene, fish adaptations would depend on temperature. If waters were slightly warmer than modern, antifreeze might be less critical, but cold adaptation would still be useful. Birds like penguins have dense feathers and fat layers. They are built to dive in cold water and return to land. So the Antarctic ecosystem was still a cold-adapted system, even if it was warmer than today in certain intervals. Now, here's something that often surprises people. A cold ocean can be more productive than a warm ocean in certain ways. Warm oceans can be clear and beautiful, but they can also be nutrient-poor in the open water, because warm surface layers can prevent mixing. Nutrients can get trapped in deep water and not reach the surface. Cold oceans, especially windy ones, often have strong mixing. That brings nutrients up that fuels plankton growth, so the Antarctic waters could support dense food webs. That means they could support large whales, and large whales could support Megalodon. Now, imagine the Antarctic shelf edge, where shallow water drops into deep water. This boundary is often a place of concentrated life. Currents flow along it, nutrients rise, fish gather, whales travel. It is also a place where predators patrol. A large shark could cruise along this edge, using deep water as cover and shallow water as a feeding zone. It could sense movement above, it could sense vibrations, it could smell blood or waste, it could wait. And because the water is darker and often cloudy, it could approach without being seen until the last moment. This is the kind of environment that makes a giant predator effective. Now, it's also worth remembering that the Miocene Antarctic ecosystem would not be exactly like today's. The species composition would differ. Some modern groups might be absent, others might be more common. For example, modern Antarctic ecosystems are heavily centered around krill. In the Miocene, the role of krill-like organisms could still be important, but the exact species and dynamics could differ. The whales of the Miocene were not identical to modern whales. Their sizes and behaviours could differ. The predators of the Miocene included animals that no longer exist, so the Miocene Antarctic Sea would feel like a familiar ocean with unfamiliar faces. Now, let's imagine what it would feel like to be in that water, surrounded by these creatures. Not swimming, because that would be a short experience, but imagine being just beneath the surface looking around. The light is dim, the water is cold, particles drift. You see fish moving in quick flashes. Then you see a whale pass by, massive and calm, moving with slow power. Its body fills your view. It doesn't look like it's trying. It looks like it belongs. Farther away you see another whale, and another. They are feeding, diving, surfacing. You hear sound through the water. Low calls, the rush of movement, the crack of distant ice. A seal darts past, fast and agile. Then the water shifts, not because you see something, but because the pressure changes. A presence moves in the deep, something large enough that the water around it feels heavier. You don't see it clearly, because the water is dim and the distance is too far, but you sense it. That is how the ocean often works. It doesn't show you everything. It lets you feel that something is there. And in a Miocene Antarctic sea full of whales, fish, seals and birds, there is room for a predator like Megalodon to exist as part of the system. Not as a legend, but as a biological reality. Now, with the creatures of the Antarctic waters in mind, we can move closer to one of the most important relationships in this world: whales and Megalodon. Because the next step is to understand why the Miocene was such a perfect time for large whales to thrive, and why that would create the ideal hunting era for the biggest shark that ever lived. If you want to understand why Megalodon became what it was, you have to understand whales. Not just that whales existed, but that whales were changing, expanding, diversifying, spreading into new habitats and becoming a bigger part of the ocean than they had ever been before. Megalodon wasn't just a giant shark that happened to live near whales. It was a predator shaped by them. Its size, its bite, its teeth, its entire role in the ecosystem makes the most sense when you picture an ocean where large marine mammals were becoming common enough to support a hunter that needed huge meals. And the Miocene, the main era when Megalodon lived, was exactly that kind of time. It was a period when whales were abundant, varied, and in many cases vulnerable, in ways that created opportunity for a predator built like a living wrecking ball. So when we say whales on the menu, it's not meant to be dramatic, it's meant to be honest. Because for Megalodon, whales were not rare prizes, they were the main course. And in the southern seas, including waters near Antarctica during warmer and more productive intervals, whales could have been especially important. Cold, nutrient-rich waters support large feeding grounds. Large feeding grounds attract whales. Whales attract predators. That's the chain. Now, to understand why the Miocene was such a perfect prey era, we need to look at what whales were doing at that time. Whales did not always look the way they do now. Early whales evolved from land mammals. They transitioned into the ocean over millions of years. Their bodies changed dramatically. Legs shrank. Tails became powerful. Nostrils moved to the top of the head. Hearing adapted to underwater sound. By the Miocene, whales were fully marine, and they were experimenting with different lifestyles. This is one of the reasons the Miocene is so interesting. It wasn't just a stable world with a fixed set of modern animals. It was a world where many lineages were still exploring what was possible. Some whales were becoming specialists in filter feeding. These are the ancestors of modern baleen whales, which feed by taking in water and filtering out small prey like krill and small fish. Other whales remain toothed predators, hunting fish and squid, and in some cases hunting other marine mammals, so the ocean had both types, filter feeders and hunters. For Megalodon, the filter feeders were especially important, because filter-feeding whales often gather in large numbers where food is concentrated. They can become predictable. A predator that hunts large prey benefits from predictability. If you are a small predator, you can survive on scattered prey. You can eat a fish here and a squid there. You can adapt quickly. But if you're a giant predator, you need big meals. You need prey that makes the energy cost worthwhile. You need prey that appears reliably enough to support your size. Whales provide that. A single whale contains an enormous amount of energy. Blubber alone is like fuel storage. Muscle is dense food. Blood is rich in nutrients. For a predator like Megalodon, a whale is not just food. It is survival in one event. Now, the Miocene also saw changes in whale size. Not every whale was a modern blue whale giant. Many were smaller than today's largest species, but smaller than a blue whale can still mean very large. A whale the size of a modern humpback or smaller is still a huge target. It's still far beyond what most predators could handle. Megalodon could handle it. And because the Miocene had a wide range of whale sizes, it provided a wide range of targets. Young whales, medium whales, larger whales, different species with different behaviours. This is important because predators often target the vulnerable. A newborn or juvenile whale is not as strong as an adult. It may not swim as fast. It may not have the experience to avoid danger. It may stray from the group. Sick or injured whales are also vulnerable. Even a small injury can become a problem in the ocean. Blood loss, infection, reduced mobility. A whale that cannot keep up becomes isolated. So in a whale-rich Miocene ocean, there would always be some individuals that were easier targets, and that creates a steady prey supply for a large predator. Now, let's talk about why whales were thriving in the first place. Whales thrive when the ocean is productive. Productive oceans have strong plankton blooms. They have abundant fish and krill-like organisms. They have nutrient mixing and upwelling. They have seasonal pulses that create feeding seasons. The Southern Ocean, even today, is extremely productive in certain seasons. It supports huge whale feeding grounds because of the abundance of krill. In the Miocene, Antarctic waters could also be productive, especially during warmer intervals when open water seasons were longer and coastal shelves were accessible. So whales would have reasons to feed in southern waters. They might migrate south in productive seasons, feeding heavily and building energy reserves. That means the southern seas could become crowded with whales during certain times, and crowded feeding grounds are exactly where a predator like Megalodon could appear. Not necessarily living there year-round, but showing up when the conditions were right. Now, imagine a Miocene feeding ground near Antarctica. The water is cold and dark, but full of life. Plankton blooms near the surface. Fish gather in schools. Squid move through deeper layers. Whales arrive. They surface in groups. They feed. They dive. They churn the water. The sea becomes busy. From above, you might see blows rising like small clouds. You might see backs breaking the surface. You might see birds circling, drawn by the fish that get pushed upward. From below, you would feel the vibrations of whales moving, the low-frequency sounds of their calls, the pressure waves of their bodies displacing water. Now imagine Megalodon entering this scene. It doesn't need to rush. It doesn't need to charge in like a monster in a movie. It can cruise along the edges of the feeding ground, staying in deeper water, watching. And by watching, we don't mean looking with eyes the way a human watches. We mean sensing, reading the water, detecting movement, smelling, feeling vibrations. A large predator in the ocean can learn the pattern of a feeding ground. It can learn where whales tend to surface. It can learn where the weaker individuals drift. It can choose. Now, what makes whales such perfect prey is not that they are helpless. Whales are powerful. They can fight back. They can injure predators. They can protect each other in groups. But Megalodon had advantages. Its size gave it power. Its jaws and teeth gave it cutting ability. Its bite could inflict massive damage quickly, and it likely used strategies that reduced risk. One of the most common ideas about Megalodon's hunting behaviour, based on tooth marks found on fossil whale bones, is that it targeted the fins and tail. If you disable the tail, you disable the whale's engine. A whale without full tail power cannot swim effectively. It cannot escape. It becomes vulnerable. This strategy is not unique to Megalodon. Modern predators often target mobility. A lion goes for the legs. A wolf goes for the hindquarters. A crocodile grabs and drags. In the ocean, mobility is everything. If you take it away, the fight ends quickly. So Megalodon could use a single powerful bite to turn a strong whale into a struggling one. And in cold water, struggling becomes even more dangerous. Energy drains, heat loss increases, blood loss becomes severe, the ocean takes over. Now, the Miocene was also a time when whales may not have had the same predator avoidance behaviours as modern whales. Modern whales live in a world with predators like orcas and large sharks. They have behaviours that help them avoid danger. They travel in groups. They protect calves. They use certain migration routes. In the Miocene, whales were still evolving in a world where predator pressures could be different. They faced predators, yes, but the exact predator community was not identical to today's. That means some whale species might have been less adapted to certain threats. This could make them more vulnerable. Also, whale diversity means some species were simply easier targets. Different body shapes, different swimming styles, different group behaviour. Megalodon would exploit that. Now, consider the role of whale migration. Whales do not stay in one place. Many migrate between breeding and feeding grounds. If Miocene whales migrated into southern waters seasonally, that would create predictable prey pulses. A predator that learns these pulses can time its movements. Even without human-like planning, animals can follow seasonal patterns. They respond to food availability. They follow migration routes. So Megalodon could potentially track whale movements along the southern seas, using the ocean highway we talked about earlier. Now imagine the coastline again, and imagine whales travelling along it. They follow the shelf edge. They stay in water that supports feeding. They move steadily. Some are adults, some are juveniles, some are mothers with calves. This is a moving prey field. Megalodon could patrol parallel to them, staying just out of sight, using deeper water as cover. It could strike when opportunity appears. Now, there's another reason whales were perfect prey, and it's simple. Whales are big enough to feed more than one predator. In an ecosystem, a large kill creates a feeding event. Scavengers arrive, smaller sharks gather, fish pick at scraps, birds feed at the surface, so when a whale dies, it becomes an ecosystem moment. Megalodon could feed heavily, but it wouldn't consume everything. Other animals would benefit. This is important because it means Megalodon's hunting would shape the ecosystem, not just satisfy its hunger. Apex predators influence food webs by controlling prey populations and creating feeding opportunities for scavengers. So in a Miocene ocean full of whales, Megalodon would be an ecosystem engineer in its own way. Now let's think about the whales themselves. What kinds of whales were present in the Miocene? There were early baleen whales, some of which were smaller than modern giants. There were toothed whales, including predatory forms. There were transitional species. Some whales may have had different feeding strategies than modern whales. Some may have been more coastal, some more offshore. This variety means Megalodon could hunt in multiple environments. It could hunt along coastlines where whales gather. It could hunt in open water corridors where whales migrate. It could hunt near feeding grounds where whales slow down to eat. So the Miocene ocean was like a buffet for a predator that specialised in large prey. Now what about Antarctica specifically? If Antarctic waters were productive during certain Miocene intervals, they would attract whales. The Southern Ocean today is one of the world's major whale feeding regions. That pattern likely has deep roots, because the basic conditions that make it productive, nutrient mixing and seasonal light, have existed for a long time. So in the Miocene, whales feeding near Antarctica would not be surprising, and if whales were feeding there, then the idea of Megalodon appearing there becomes more plausible, not because Megalodon liked cold water, but because Megalodon liked whales, and whales go where the food is. Now, picture the scene from the whale's perspective, just for a moment. You're moving through cold water, following a route your species has followed for generations. The sea is rich with prey. You dive and feed, you surface and breathe. The world feels open and endless, but the ocean is not empty. The ocean. Below you, in deeper water, there is movement you cannot see. The water carries signals, but you don't know how to interpret them. The pressure shifts slightly. The soundscape changes. Then, suddenly, there is impact. Not a gentle bump, a violent force, a bite that targets your tail or fin. A tearing, crushing sensation. Pain that spreads through the body like fire, even in cold water. The ability to swim weakens. The body slows. The group moves ahead. The ocean becomes larger and lonelier in an instant. This is the reality of predator-prey relationships in the sea. And it's part of why Megalodon could grow so large, because the prey was large enough to support it. Now, as we move forward, we need to look more closely at Megalodon itself. Not the myth version, not the movie monster, the real animal, as far as we can reconstruct it from teeth, fossils, and ecological clues, how it lived, how it moved, how it hunted. Because once you understand Megalodon's lifestyle, the idea of it moving through the southern seas near Antarctica becomes less about imagination and more about ecology. A predator doesn't appear in a place because it looks dramatic. It appears because the environment offers the right conditions. And in the Miocene, whales created those conditions. They were the perfect prey area. And the ocean, especially in productive regions like the southern seas, was ready to support a hunter that could take advantage of it. If you could take one step out of the modern world and into the Miocene ocean, the first thing you would probably notice is how ordinary it feels. Not ordinary in the sense that you'd feel safe, because you absolutely would not, but ordinary in the sense that the ocean doesn't announce what era it belongs to. It doesn't come with labels. It doesn't look like a museum exhibit. It looks like water, wind, and movement, doing what they've always done. And that's important, because Megalodon's life down south near Antarctica would not have been a special story in its own mind. It would not have felt like a dramatic adventure. It would have been a practical decision shaped by food, temperature, and opportunity. Megalodon didn't migrate because it wanted to explore. It migrated because the ocean rewarded movement. If prey was abundant in southern waters during certain seasons or warmer intervals, then the far south would become part of its world, not as a permanent home, but as a hunting range. So when we talk about Megalodon's life down south, we're really talking about how a giant predator would behave in a cold, productive ocean at the edge of the planet. We're talking about travel, hunting, energy, competition, risk, and the quiet logic of survival. The first thing to understand is that Megalodon's lifestyle was built around efficiency. A predator that large cannot afford to waste energy constantly. It cannot sprint everywhere. It cannot chase small prey endlessly. It needs large meals. It needs periods of calm movement. It needs a strategy that allows it to feed well and then travel without constant hunger. Modern large sharks do something similar. They cruise, they patrol, they conserve energy, they make decisions that look slow but are actually smart. Megalodon's body would have been shaped for that kind of life. A large shark's tail provides powerful propulsion, but its movement is not usually frantic. It is steady, it is controlled, it uses momentum. So if Megalodon entered southern waters, it likely did so with calm purpose. It would follow the same patterns that whales followed, because whales were the main prey. It would move along migration corridors. It would patrol feeding grounds. It would linger where food was concentrated. Now, think about the difference between living in warm tropical water and living in cooler southern water. Warm water affects metabolism differently than cold water. In cold water, many animals slow down. Their muscles perform differently. Their energy use changes. For a shark, temperature matters. But Megalodon may have had an advantage if it had some ability to maintain body warmth in key regions, similar to modern great white sharks and some other large predatory fish. This is not the same as being fully warm-blooded like a whale, but it can make a big difference. If Megalodon could keep its muscles and brains slightly warmer than the surrounding water, it could remain active and effective in cooler environments. That would allow it to follow prey into temperate and even colder zones, especially during warmer climate phases. So Megalodon's life down south would not necessarily mean it lived in near-freezing conditions year-round. It could mean it entered southern waters when conditions were suitable and prey was present. It could also mean it stayed near temperature boundaries, using the mixing zones where cold and milder water met. Those boundaries are often rich in life. Now, imagine Megalodon approaching Antarctica. Not the modern ice wall, but the Miocene coastline we've been building. A coast with exposed rock in places, with glaciers in others, with bays and shelf edges that support feeding grounds. The water is cold but productive. Whales are present in certain seasons, feeding heavily. Fish are abundant. Smaller predators patrol. The ocean is full of information. In this environment, Megalodon would not need to be everywhere. It would need to be in the right places. A large predator learns patterns through experience. It learns where prey gathers. It learns where prey travels. It learns where hunting is successful. So Megalodon's southern life would likely revolve around key zones, shelf edges, feeding grounds, migration corridors. It would patrol those zones like a silent presence. Now let's talk about hunting behaviour, because that's the part people are most curious about, even if they don't admit it. How does something that big actually hunt? It doesn't hunt like a movie monster. It doesn't jump out of the water with its mouth open in slow motion. That kind of behaviour is rare and risky, even for modern sharks. A giant predator survives by reducing risk. The best hunt is the one where the prey is disabled quickly, and the predator is not injured. In the ocean, injury can be fatal. There is no rest, no shelter, no easy recovery. If you cannot swim well, you die. So Megalodon's hunting strategy would likely focus on high-impact attacks that end the struggle fast. Evidence from fossil whale bones with bite marks suggests Megalodon targeted areas like fins, tails, and sometimes the rib cage. These are places where a bite can cause catastrophic damage. A tail bite can cripple movement. A fin bite can destabilize swimming. A rib cage bite can damage vital organs. In southern waters, where the sea might be darker and visibility lower, Megalodon could approach from below and behind. It could strike once with massive force, then wait. That waiting is important. Modern large sharks sometimes bite prey and then back off, allowing the prey to weaken from blood loss. This reduces risk. The predator avoids a prolonged fight. Megalodon could do the same. In cold water, blood loss and stress can weaken prey quickly. A whale that is injured becomes slower. It becomes separated. It becomes vulnerable. So Megalodon's hunting in the south might involve a strike and then a slow follow. Not a chase, a follow. Now what about the daily life of Megalodon when it wasn't hunting? It would still move. Large sharks don't stop. They have to keep water moving over their gills to breathe efficiently, though some sharks can rest more than others depending on species. A giant active predator would likely keep cruising most of the time, so Megalodon's southern life could look like long periods of steady movement through deep water, with occasional rises toward the surface when prey activity was detected. It might move along the shelf edge, where depth drops away. It might circle feeding grounds at a distance. It might travel between hotspots of productivity. This is a life of patience. Now, let's talk about how Megalodon might have used depth. Depth is a tool. In deep water, light fades quickly. The surface becomes a bright ceiling. From below you can see silhouettes of animals above you. From above you can't see into the darkness. This is one of the simplest hunting advantages in the ocean. So Megalodon could use depth to stay hidden. It could also use depth to manage temperature. Deeper water is colder. If Megalodon needed to cool down after feeding, or after moving through warmer surface layers, it could descend. If it needed to stay warmer, it could remain in shallower water during warmer seasons. So depth is not just hiding, it is regulation. Now consider the prey behaviour in southern waters. Whales feeding near Antarctica might dive deep to feed, then surface to breathe. They might spend time near the surface during rest. They might travel in groups. A predator could take advantage of these rhythms. It could wait near the surface during feeding activity. It could patrol below the group. It could strike when a whale surfaces alone. So Megalodon's southern life would be tied to whale behaviour. Now what about young megalodons? This is where the southern story becomes more uncertain, but still interesting. Large sharks often use nursery areas for their young. These are safer, shallower environments where young sharks can grow with less risk from large predators. For Megalodon, nurseries were likely in warm, shallow coastal waters because young sharks would struggle in very cold conditions and would be vulnerable to predators. So it's unlikely that Antarctica itself was a nursery region for Megalodon. Instead, the southern seas would likely be part of the adult range, where large individuals travelled to hunt. That means Megalodon's life down south would mostly involve mature animals, large, experienced hunters. This matters because adult Megalodons would be more capable of handling colder water, long travel distances, and large prey. Now let's talk about competition again, because the Southern Ocean was not a private hunting ground. Other predators would be present. Large-toothed whales could hunt marine mammals and fish. Smaller sharks could scavenge. Other large sharks could compete for prey. Even if Megalodon was the biggest, it still had to deal with the fact that the ocean is shared. So Megalodon's southern life might involve avoiding unnecessary conflict. It could feed quickly and then leave. It could target prey in areas where competition was lower. It could patrol wider ranges. Large predators often dominate through presence, but they still avoid fights that could injure them. So the life of Megalodon down south would be powerful but not reckless. Now, imagine the seasonal rhythm again. In summer, the southern seas are bright for long hours. Productivity increases. Feeding grounds become active. Whales arrive. Megalodon could follow. In winter, darkness increases. Sea ice expands. Whale presence might drop. The ocean becomes less predictable. Megalodon could move north again, following prey into milder waters, so its southern life might be seasonal, tied to the pulse of the Antarctic ecosystem. This is similar to how many modern predators behave. They follow prey, they follow seasons. Now picture a mature Megalodon cruising along the Antarctic shelf edge in a productive season. It moves steadily through cold water. Its body is massive, but its movement is smooth. It doesn't thrash. It doesn't waste energy. It senses whale activity ahead. Low-frequency sounds travel through the water. Vibrations carry. The smell of life is stronger in the current. It rises slightly, staying below the surface. The light above is pale and broken by waves. It sees silhouettes of whales, large bodies moving slowly, some diving, some surfacing. It waits. Then it chooses a target. A whale that is slightly separated. A younger whale. A whale that surfaces late. The shark accelerates. Not in a frantic sprint, but in a powerful surge. The tail drives forward. The body becomes a missile. The bite is not a test. It is a commitment. Teeth designed to cut and crush, tear into flesh. The impact sends shock through the prey. The water fills with movement. Then the shark pulls away, leaving the prey injured. It follows at a distance, letting the ocean do part of the work. Blood spreads. The prey weakens. When the moment is right, the shark returns. This is not a chase. It is a controlled hunt. And in a cold, productive southern sea, this strategy would be effective. Now, after feeding, Megalodon would likely spend time digesting. Large meals take time. Sharks can go long periods without eating after a big feed. Digestion is slow, especially in cooler water, so Megalodon might descend into deeper water, moving slowly, letting its body process the meal. It might travel while digesting, using currents to move. It might avoid unnecessary activity. This is part of its life that people rarely imagine, but it matters. Most of a predator's life is not hunting. It is waiting, moving, and conserving energy. So Megalodon's southern life would be mostly quiet. Quiet movement in deep water. Quiet patrols along shelf edges. Quiet presence beneath feeding grounds. The drama would be rare, but intense. Now, one more thing about Megalodon down south is that the environment itself could shape its behaviour. Cold water can preserve scent trails longer. Currents can carry information farther. The dim light can make ambush easier. So southern waters could offer hunting advantages. At the same time, cold water could increase energy cost for maintaining activity, depending on Megalodon's physiology. So Megalodon would need the payoff to be worth it. That payoff would be whales. And if whales were abundant in the southern seas during certain intervals, then Megalodon's life down south becomes a logical part of its range. Not a permanent Antarctic resident, but a seasonal giant passing through, using the southern seas as a hunting corridor when the ecosystem was rich enough. Now, as we move forward, we need to get even closer to the hunting itself, because Megalodon didn't just hunt in any water, it hunted in water that had currents, depth changes and darkness. And the next piece of this story is about what hunting looks like when the environment is shaped by cold currents and shadowy depths. Because in the southern seas, the ocean isn't just a surface, it's a layered world. And the deeper you go, the more it becomes a place where a predator like Megalodon could disappear completely, even while it was right there. The ocean is honest in a way that land is not. On land, you can hide behind a tree, you can crouch behind a rock, you can disappear into tall grass, you can break line of sight and feel safe for a moment. In the ocean, there is nowhere to stand, nowhere to lean, nowhere to truly stop. Everything that lives there is suspended in the same space. The water is the floor, the ceiling, and the air all at once. And yet the ocean is also full of hiding places. Not physical hiding places like caves and forests, but hiding places made of light, depth, and movement. Hiding places made of temperature layers and currents. Hiding places made of darkness that begins just a few meters below the surface. This is the world Megalodon would have hunted in, especially in the southern seas. Cold currents, shadowy depths, water that carries sound and scent for long distances, water that can be crowded with life in one moment and feel empty in the next. And in that environment, hunting is not a chase, it's a process. It's positioning, timing, patience. It's knowing how to use the ocean itself as part of your strategy. So let's step into that world and look at what hunting could have looked like for Megalodon near Antarctica, when the sea was cold, the light was dim, and the currents never stopped moving. First, we need to talk about cold currents, because cold currents are not just cold water moving from one place to another. Cold currents are structure. They are highways of water with different temperature, different salinity, and different density. They create boundaries in the ocean where water masses meet. Those boundaries can trap nutrients, they can concentrate prey, they can shape migration routes. In the Southern Ocean, currents are powerful and persistent. They circle Antarctica, connecting the world's oceans. Even in the Miocene, the southern seas would have been influenced by strong circulation patterns. That means Megalodon's hunting environment was not static. It was moving under it, around it, and above it. Now, cold water behaves differently than warm water. Cold water is denser. It holds more dissolved oxygen. It can feel heavier, almost thicker, even though it's still water. For marine life, cold water can be a challenge because it can slow muscle performance. But it can also be a benefit because it supports rich ecosystems through mixing and oxygen availability. So cold currents could bring both difficulty and opportunity. For prey animals like whales, cold currents can mark feeding zones. Nutrient-rich water supports plankton. Plankton supports fish and krill-like organisms. Whales follow food. So whales may concentrate near cold current boundaries where feeding is best. For Megalodon, that means cold currents could act like signposts. Not visual signposts, but sensory ones. A shark can detect temperature changes. It can sense differences in water chemistry. It can feel shifts in movement. So Megalodon could move through the ocean and recognise when it entered a zone that was more likely to hold prey. Now the next thing to understand is that currents create predictable patterns of movement for prey. If you're a fish, you might move with the current to save energy. If you're a whale, you might travel along current edges where food is concentrated. If you're a seal, you might hunt where currents push prey into certain areas. So prey movement is often shaped by currents, and predators learn this. A predator doesn't need to know a map, it needs to know patterns. If a certain shelf edge always has strong upwelling, it will always be productive. If a certain current boundary always concentrates prey, it will always be busy. So Megalodon's hunting could involve returning to the same kinds of zones again and again. Now let's talk about shadowy depths, because this is where the ocean becomes truly different from what most people imagine. Light does not travel far in water. Even in clear water, light fades quickly. In productive water, full of plankton and particles, it fades even faster. In the southern seas, where the sky can be cloudy, the sun can be low and the water can be dark, the world below the surface could become dim within a short distance. That means depth is darkness, and darkness is cover. A large predator can use that cover to approach prey without being seen. This is one of the most powerful advantages in marine hunting. From below, you can see silhouettes against the surface light. From above, you cannot see into the deep. So a predator like Megalodon could position itself beneath a group of whales, watching their movement as shadows overhead. It could choose its moment. It could rise quickly, strike, and then drop back into darkness. This kind of hunting does not require speed over long distances. It requires short bursts of power. A large shark can do that. Now think about the prey's perspective. A whale at the surface is focused on breathing. It might be resting. It might be feeding. It might be travelling. It cannot constantly look down into the deep. Even if it did, it might not see anything, because the water below is dark. So the whale's main defence is awareness, group behaviour and movement. But awareness is limited in the ocean. You can hear sounds, but the ocean is full of sound. You can feel movement, but the ocean is full of movement. So the deep offers predators an advantage. Now, there's another factor that makes shadowy depths even more useful: temperature layering. The ocean often has layers of different temperature. A warm surface layer can sit above colder deep water. The boundary between them is called a thermocline. Crossing a thermocline can feel like crossing an invisible wall. The temperature changes suddenly. The density changes. The sound behaviour changes. Predators can use these layers. In some cases, prey animals may prefer certain temperature layers for comfort or energy efficiency. Fish might gather in a layer where food is abundant. Whales might dive to a certain depth repeatedly, because that's where prey is concentrated. So a predator can position itself near these layers, waiting. Also, thermoclines can affect visibility. Light behaves differently in different layers. Particles can concentrate at boundaries. The water can look hazier, so these layers can create natural camouflage. Now add the movement of currents to this layered darkness. The ocean becomes a three-dimensional hunting ground, with shifting walls and corridors made of water. Megalodon could use these corridors. It could travel along deep channels, staying hidden. It could move along the shelf edge, where the bottom drops away. It could rise into shallower water when prey is present. Now consider the shelf edge again, because the shelf edge is one of the best hunting zones in the ocean. It is where shallow feeding grounds meet deep escape routes. It is where whales travel. It is where fish gather. It is where currents often push nutrients upward. So the shelf edge is a feeding zone and a travel zone at the same time. For a predator, that's ideal. Megalodon could patrol the shelf edge, moving parallel to it, staying just deep enough to remain unseen. When whales feed on the shelf, the predator is nearby. When whales travel along the edge, the predator can follow. Now, hunting in cold currents also means dealing with energy costs. Cold water can slow digestion. It can affect muscle efficiency. A predator might need to balance activity with rest. So Megalodon would not be constantly attacking. It would pick its moments. A large predator can afford to wait because when it feeds big. So the hunt is often a waiting game. Now let's imagine a hunting scenario in these southern waters. It's a productive season. Whales are feeding near the shelf. The water is dark and full of plankton. The surface is rough with wind-driven waves. Below the surface, the light fades quickly. Megalodon is cruising in deep water along the edge of the shelf. It is not rushing. It is moving steadily using the current. It senses the presence of whales ahead. The water carries low-frequency sound. It carries the vibrations of large bodies moving. The predator rises slightly, staying below the surface light. It positions itself beneath the feeding area. Above, whales dive and surface. Some are closer together, some drift farther apart. The predator waits. Then one whale surfaces slightly away from the group. It may be young. It may be tired. It may simply be out of position. The predator moves upward with a burst of power. The strike is fast but not chaotic. It is controlled. The jaws close on a fin or tail. Teeth cut deep. The force is enormous. Then the predator releases and drops back into darkness. The whale is injured. It struggles. It loses speed. The group may react, but the ocean is noisy and confusing. The injured whale falls behind. The predator follows at a distance, letting the cold water and blood loss weaken the prey. When the prey slows enough, the predator returns to feed. This is not a scene of constant thrashing. It is a scene of efficiency. Now, hunting in shadowy depths also involves dealing with other predators. A large kill attracts attention. Smaller sharks might arrive to scavenge. Large predatory whales might investigate. Fish gather to feed on scraps. Megalodon would likely dominate the feeding event, but it would still be aware of competition. It might feed quickly and then leave. It might return later when the competition is gone. It might move the prey into deeper water to reduce interference. This is something modern sharks sometimes do. They pull prey away from the surface to feed in calmer, safer water. So Megalodon's hunting could involve moving prey into deeper zones. Now, consider the role of currents during feeding. Currents can carry blood and scent far. They can draw scavengers from a distance. They can also disperse the scent trail, making it harder to track. So the ocean's movement shapes the feeding event. Megalodon would be operating in an environment where nothing stays in one place. Even the evidence of a kill, blood, movement, sound is carried away by the water, so the predator must act within a moving system. Now let's talk about the emotional side people imagine, because it's easy to picture hunting as dramatic, but in reality hunting is routine. For Megalodon, hunting was not a moment of excitement, it was a necessity. A giant predator does not hunt for fun, it hunts because it must. So the southern seas would be part of its routine range, a place it enters when conditions are right, a place it leaves when prey moves on. Now the shadowy depths near Antarctica would also have another feature, cold stability. Deep water temperatures are often stable compared to surface temperatures. Surface water can warm and cool with seasons and weather. Deep water stays more consistent. So for a large predator, deep water can be a stable environment. It can be a place to rest while still moving, a place to digest, a place to travel without dealing with surface turbulence. So Megalodon's southern life could involve long periods in deep, cold water, using the depths as a highway beneath the highway. Now, if you think about it, this makes Megalodon feel less like a monster and more like a realistic animal. It wasn't constantly attacking. It wasn't constantly visible. It was mostly hidden. It was mostly moving through darkness. It was mostly doing what large predators do, waiting. Now, there is one more element that makes hunting in southern waters especially interesting. The southern seas can have strong seasonal changes in light. In long daylight seasons, the surface is bright for extended periods. That can make silhouettes more visible from below, which helps predators hunting from depth. In darker seasons, the surface is dim, which might reduce silhouette clarity but also reduce prey visibility overall. So hunting conditions could change through the year. Megalodon could take advantage of times when prey was abundant and the environment offered the best hunting conditions. Now, as we move forward, we're going to shift from the mechanics of hunting to the feeling of the ocean itself, because hunting doesn't happen in silence. The ocean is full of sound, full of vibration, full of subtle noise that tells animals what is happening even when they cannot see it. And in the Miocene southern seas, the soundscape would have been different from today's, because there were no engines, no sonar, no human noise, just water, wind, animals, and ice. So next, we're going to listen to that world, the sounds of the Miocene Antarctic Ocean, the calls, the movement, the hidden noise of life, and how a predator like Megalodon would have lived inside that sound without ever needing to be seen. If you close your eyes and imagine the ocean, you might hear waves first. That's the sound most people think of, the surface sound, the rhythm of water meeting water, or water meeting shore, the steady crash, the hiss of foam, the pullback of the tide. But the ocean is louder than that. It's louder in a way that doesn't always reach your ears from the surface, because so much of it happens below. The ocean is full of sound that travels farther than it would in air, sound that can move for kilometres, sound that can pass through darkness and distance like it belongs there. And in the Miocene, the ocean was even more honest about its own voice. There were no engines, no sonar pings, no distant hum of ships, no mechanical noise creeping into the water from above. There was only the planet's natural soundscape, wind, waves, ice, animals, currents, the quiet friction of water moving over itself. So if you want to understand what it felt like to exist in those waters, especially near Antarctica during Megalodon's time, you have to understand what it sounded like. Because in the ocean, sound is not decoration. Sound is information. Sound is location. Sound is warning. Sound is opportunity. For whales, sound is communication. For prey, sound is danger. For predators, sound is a map. So let's step into the Miocene Southern Sea and listen carefully. The first sound is the wind. Above the surface, wind would be constant in the southern latitudes. The air moves in long, persistent patterns. Storm systems sweep through. The ocean's surface is rarely still. Wind creates a steady roar. Not always loud like a storm, but always present. A moving pressure in the air. When wind strengthens, it changes everything. It builds waves, it throws spray. It makes the surface chaotic, and that chaos becomes sound. The surface becomes a field of noise. Waves crash, foam hisses, water slaps against itself. If you were standing on a Miocene Antarctic coastline, you would hear that sound first. The surface voice of the sea. But if you went underwater, the sound changes. Underwater, waves don't sound like they do above. They become a deep rumble, a constant rolling noise. The impact of waves creates pressure changes that travel through the water. Even when the surface looks calm, the underwater world carries a low background hum of movement. And in the Southern Ocean, that hum would be strong, now had ice. Even in warmer phases of the Miocene, Antarctica still had ice. Glaciers still reached the sea in some places, icebergs still carved. Sea ice likely formed seasonally. Ice has its own sound. It cracks, it pops, it groans. When ice expands and contracts with temperature changes, it makes sharp snapping sounds. When a glacier shifts, it creaks like something heavy moving slowly. When an iceberg breaks, it can sound like thunder underwater. Icebergs also make a strange fizzing sound as they melt because trapped air bubbles escape. If you were underwater near an iceberg, you might hear a constant crackle, like static as tiny bubbles release and rise. So the Miocene Southern Sea would not be silent. It would be full of these ice noises, especially near the coast. Cracks, pops, distant booms, and those sounds travel. A whale could hear ice breaking from far away. A predator could hear it too. Now, add the sound of currents. Currents don't have a single obvious noise, but they create sound through movement. Water moving over the seafloor creates a low friction sound. Water moving around rocks creates turbulence, a soft rushing noise. In narrow channels, currents can become fast and loud, like an underwater river. In the Southern Ocean, currents would shape the soundscape by creating constant background movement. This matters because animals listen for changes. A constant background noise becomes normal, but a sudden change stands out. A burst of movement, a splash, a struggle. Now let's talk about the creatures, because this is where the Miocene ocean becomes truly alive. Start with fish. Fish are not silent. Schools of fish create a faint collective sound as they move, a soft rustle in the water. Some fish also produce sounds intentionally, using muscles and swim bladders to create clicks, grunts or hums. In the Miocene, fish species would differ, but the ocean would still carry fish sounds. Small, quick noises, movement shifts, the sudden rush of a school turning. Squid and cephalopods are quieter, but their movement still disturbs the water. When they jet away, they create a sudden pulse of motion, so even small animals add to the soundscape. Now, seals and seal-like animals, they splash at the surface. Underwater, they move fast and their bodies create pressure waves. They can vocalize too, producing calls and noises that travel through the water. If seals were present near Antarctica in the Miocene, they would add sharp, energetic sounds to the environment. Fast movement, quick bursts, occasional calls. Now, whales. Whales are the main voice of the ocean. Even today, if you listen to recordings of whale calls, you can feel how much space they fill. Low-frequency sounds that travel for kilometers. Complex songs, clicks and pulses. In the Miocene, whales were present, and many would have been vocal. Baleen whales produce low-frequency calls. These can travel enormous distances. They are used for communication, navigation, and possibly coordinating movement. Toothed whales produce clicks and whistles. Clicks can be used for echolocation, allowing them to see with sound. Whistles can be used for communication. So the Miocene ocean would have been full of whale sound. Not constant like a loud concert, but present like a living background. A low call here, a distant pulse there, sometimes overlapping, sometimes fading away into silence. Now imagine a whale feeding near the Antarctic shelf. It dives. Its body moves through the water like a slow machine. It exhales at the surface, a burst of air that becomes a sound above and below. Underwater, you hear the rush of its movement, the slow sweep of its tail, the low vibrations of its body. If multiple whales are feeding, the soundscape becomes layered. You hear calls, you hear movement, you hear the occasional slap of a tail at the surface. The ocean becomes crowded with sound. Now, think about how Megalodon would experience this. A shark does not hear in the same way a whale does, but it senses vibration extremely well. Sharks have systems that detect pressure changes and movement in the water. They can feel low-frequency vibrations. So Megalodon would live in a world where sound is not just heard, but felt. A whale call might be felt as a deep vibration. A struggling animal might create frantic pressure waves. A feeding event might create a constant disturbance. So Megalodon could use the soundscape as a guide. It could detect where whales are feeding. It could detect when prey is panicking. It could detect when a large animal is injured and moving irregularly. This is important because in dark, cloudy water, sound and vibration can be more reliable than sight. So the Miocene ocean soundscape would be part of Megalodon's hunting toolkit. Now, let's talk about the sound of predation, because it's not something people often imagine. Predation in the ocean is loud, but not always in the way you expect. There is no screaming. There is no roar. There is impact, a sudden burst of movement, a thrash of water. a shock wave. If a whale is bitten, it may thrash, it may slap the surface, it may dive suddenly, it may call out. The water becomes chaotic. That chaos produces sound, it produces vibration, and those signals travel. Other predators might detect it, scavengers might detect it, whales nearby might detect it. So a hunting event is not private. It is an announcement, not an intentional one, but an unavoidable one. Now imagine a Miocene feeding ground. Whales are feeding, the ocean is full of low calls and movement noise, birds dive at the surface. Then, suddenly, a disturbance. A whale thrashes, the surface erupts, a deep shock wave moves through the water, the soundscape changes instantly. Nearby whales react. Some dive, some move away. The feeding pattern breaks. In the deep, other animals detect the disturbance. Megalodon, if it is the one that attacked, feels the result. If it is not, it still knows something has happened. Because the ocean carries the news. Now, there is another sound in the Miocene ocean that is easy to overlook. The sound of silence. Not total silence, because the ocean is never truly silent, but stretches of quiet where the major noises fade. In deep water, far from feeding grounds, the soundscape can become minimal. You hear only the distant rumble of the surface, the faint movement of currents, the occasional crack of ice. In those quiet stretches, any new sound stands out. A whale call in the distance becomes a beacon. A sudden burst of fish movement becomes a sign of danger. So silence is part of the ocean's rhythm. And for a predator like Megalodon, silence could be useful. It could move through quiet water, listening for signs of prey. It could patrol without needing to see. Now, think about how different this soundscape is from the modern ocean. Today, human noise is everywhere. Ships, engines, sonar, industrial activity. The ocean is filled with mechanical hum. In the Miocene, none of that existed. So animal sounds would carry farther and be clearer. Whale calls would travel without interference. The sound of ice breaking would be more distinct. The natural noise of the sea would dominate. That means the Miocene ocean would feel more alive, more connected through sound. Animals could communicate over longer distances. Predators could detect prey movement from farther away. The entire ecosystem would be linked by vibration. Now, imagine what it would feel like to be beneath the surface in the Miocene Southern Sea, listening. You hear the distant rumble of waves above. You hear a faint crackle of melting ice nearby. You hear the slow pulse of currents. Then, far away, a low whale call. It is not loud, but it is deep. It travels through your body more than through your ears. It repeats. Another call answers. The sound fades, then returns. You drift in this sound field and you realize something. The ocean is not empty space. It is a medium filled with signals, and Megalodon would live inside those signals. It would not need to see everything. It would not need to rush. It could move through the depths, guided by the ocean's voice. Now, as we continue, we're going to bring the soundscape into the reality of weather and seasons. Because sound changes with storms, it changes with sea ice, it changes with the long polar light and long polar dark. The ocean is not the same in summer as it is in winter. It is not the same in calm weather as it is in a storm. And the Miocene southern seas would have had their own pattern of seasons, storms and shifting light. So next we're going to step into that rhythm. Storms, seasons and long polar light, and how they shaped the experience of the Antarctic world while Megalodon was still alive somewhere beneath the surface. If you've never experienced a place with extreme seasons, it's hard to understand how much they change everything. Not just the temperature, not just the weather, everything. The way the air feels, the way the ground behaves, the way the ocean looks, the way animals move, the way time seems to pass. In most places, day and night are reliable. The sun rises, the sun sets, and your body learns the rhythm without you even thinking about it. In Antarctica, that rhythm breaks. And it didn't just break in the modern world. It broke in the Miocene too, because Antarctica was still Antarctica. It was still sitting at the bottom of the planet, tilted into long summers of light and long winters of darkness. So when we talk about storms, seasons, and long polar light during the time Megalodon was alive, we're talking about the rhythm that shaped the entire environment. We're talking about the schedule the ocean followed, and in the southern seas that schedule mattered because it decided when life exploded into abundance and when it tightened into survival mode. It decided when whales arrived to feed, when predators followed, and when the ocean became quieter again. So let's build the year in your mind, not as a calendar, but as a living cycle of light, wind, and water. Start with the long polar light, because that is the foundation. In the Antarctic summer, the sun does not behave like it does in most places. It stays up, it circles low, it refuses to give you a clean ending to the day. This kind of light is strange. It can feel energizing at first, because it makes the world feel open. It gives you long hours of visibility. It stretches the day out until it almost feels like time has slowed down. But it can also feel unsettling, because the sky doesn't signal rest. The light keeps coming. Your body doesn't get the same cues. In the Miocene, the long polar light would have done the same thing. The sun would circle around the sky, low and steady. Shadows would stretch across the land. The ocean's surface would catch the light and throw it back in sharp flashes. And this long light would feed the ocean. Sunlight is fuel for phytoplankton. The more light available, the more opportunity for growth, as long as nutrients are present. In the Southern Ocean, nutrients are often abundant because of mixing and upwelling. So when the long summer light arrives, it can trigger huge blooms. The water can change colour. It can shift toward greenish tones in productive zones. It can become dense with microscopic life. And that microscopic life is the beginning of everything. It feeds zooplankton. Zooplankton feeds fish. Fish feeds larger predators. Whales arrive to take advantage of the feeding season. So the long polar light is not just a sky feature. It is the engine of the ecosystem. Now, in a Miocene Antarctic summer, the feeding season could be intense. If the climate was warmer than modern in certain intervals, open water could last longer. Sea ice could retreat farther. Coastal shelves could be accessible for extended periods. That means the feeding season could stretch. Whales could have more time to feed, more time to build energy reserves, more time to gather in productive zones. And if whales stayed longer, predators had more opportunity. So the summer light could create a long window of abundance. Now let's talk about storms, because the Southern Ocean is not a calm place, even in summer. Storms are part of the southern rhythm. The winds that circle Antarctica can build strength over huge distances. There is less land to interrupt them. Storm systems can form and move quickly. In the Miocene, the Southern Ocean would still have had strong winds and frequent storms, because the basic geography still allowed for it. But the details of storms could differ depending on climate. A warmer world can hold more moisture. That means storms can carry more water. They can bring heavier precipitation. They can create thicker cloud cover. So in the Miocene, coastal Antarctica could experience storms that bring heavy snow, sleet, or even rain in milder periods. Rain is an interesting detail because it changes the land and sea connection. Rain increases runoff. It carries sediment and nutrients into coastal waters. It can trigger pulses of productivity. So storms could feed the ocean in multiple ways. They also create mixing. Strong winds churn the surface. They break up water layers. They bring nutrients from deeper water up to the surface. This is one of the reasons stormy seas can be productive. They stir the system. So storms, while harsh, can be part of the reason the Southern Ocean supports so much life. Now, storms also change visibility. In calm weather, the surface might reflect the sky like a mirror in places. You might see distant whales. You might see birds feeding. In stormy weather, the surface becomes chaotic. Waves build, spray fills the air, the horizon disappears. From above, the sea looks dangerous. but below the surface, the world can be calmer. This is one of the strange truths of the ocean. Storms are loud and violent at the surface, but deeper down the water can remain relatively stable. For a predator like Megalodon, storms could provide cover. Surface chaos makes it harder for prey to see threats. It makes it harder for prey to coordinate. It can separate individuals. It can also create confusion in sound and vibration, because the surface noise increases, so storms could be hunting opportunities. At the same time, storms could also make hunting more difficult, because prey might dive deeper or move away. Whales might change behaviour. So storms are not automatically good or bad for a predator. They are conditions to navigate. Now, let's think about the seasonal transition. As summer progresses, the light begins to shift. It doesn't suddenly turn to darkness. It slowly changes. The sun's circle lowers. The angle of light becomes softer. The air begins to cool. The ocean responds. Plankton blooms peak and then decline. Fish movement changes. Whales may begin to move away. Depending on migration patterns, the feeding season begins to close. Now the autumn in Antarctica is not like autumn in a temperate forest. There are no leaves turning red. There are no gentle breezes. It is a tightening. The sea begins to cool. The air becomes sharper. Storms can become more frequent. Sea ice may begin to form again in some regions. The light continues to fade. And then winter arrives. The long polar dark. This is where Antarctica becomes truly extreme. The sun disappears for long periods. The sky becomes dim. Twilight can last, but full daylight may not return for weeks. In the Miocene, winter darkness would still be the same, because the tilt of the Earth does not change. So even in a warmer climate phase, the winter would still bring long darkness, and darkness changes the ocean. Without sunlight, phytoplankton cannot grow. Surface productivity drops. That doesn't mean the ocean becomes empty, but it becomes less abundant at the surface. Sea ice can expand. It can cover large areas depending on temperature. Animals respond. Many whales would likely migrate away from the far south during winter, moving toward milder waters or toward breeding grounds. Some animals remain, especially those adapted to cold and ice. Fish may stay in deeper water. Seals may remain if ice provides haul-out platforms. Birds may migrate or adapt depending on species, so winter is a different world. For Megalodon, winter conditions near Antarctica would likely be less favourable, because prey availability would drop if whales leave. A giant predator depends on large prey. If large prey is seasonal, the predator must be seasonal too. So Megalodon's southern presence would likely peak in the productive seasons and decline in winter. This makes sense ecologically. Now imagine the winter sea. The surface is darker, the wind is colder, ice forms, the soundscape changes. Ice cracking becomes more common. The surface noise might be reduced in some areas because ice dampens waves. But storms can still rage, the ocean feels heavier, and the long darkness changes how everything looks. In summer, the ocean surface can glitter for hours. In winter, the surface can look like a dark sheet, broken by ice and foam, so the environment becomes less visually active, but it remains physically active. Now think about the effect of long light and long dark on animal behaviour. Animals in polar regions often have seasonal rhythms that are tied to light. Feeding seasons, breeding seasons, migration timing. In the Miocene, whales likely followed these rhythms too. They would arrive in productive seasons to feed. They would leave when the feeding season ends, so the long polar light creates a predictable schedule for prey. And predators follow prey. So Megalodon's hunting opportunities would be tied to these seasonal pulses. Now storms can happen in any season, but their character changes. Summer storms might bring heavy rain or wet snow in milder conditions. They might be intense but not as brutally cold. Winter storms might bring blizzards, strong winds, extreme cold, thick cloud cover. In winter, storms can make the environment feel completely hostile. So the southern seas would have periods of calm productivity and periods of violent weather. Now imagine a day in the Miocene Antarctic summer. The sun is low but constant. The water is busy, whales feed, birds circle, a storm begins to build, clouds thicken, wind strengthens, the surface becomes rough. Whales may continue feeding at first, but as the storm intensifies, they might change behaviour, they might dive deeper, they might move away from the most turbulent surface zones. Predators like Megalodon could use the storm to approach more easily, because surface visibility is reduced and prey is distracted. So storms and feeding seasons overlap, creating complex conditions. Now imagine a day in the winter. The sky's dark, the wind is sharp, ice forms on the surface. The ocean is quieter in terms of a large animal presence, but not silent. Ice cracks. Currents move under the ice. Fish and smaller animals continue their lives below. The world feels closed. This is not a place where a giant predator would want to linger without good reason, so the winter would likely push Megalodon away, back toward milder waters where prey remains available. Now think about the long-term seasons, not just yearly seasons. The Miocene itself had climate shifts over millions of years, warmer phases and cooler phases. During warmer phases, the feeding season near Antarctica could be longer, open water could extend farther, coastal productivity could increase. During cooler phases, sea ice could expand. Feeding grounds could shrink. Whales might feed farther north. So Megalodon's southern opportunities would expand and contract over long time scales as well. This is important because it means the southern seas were not always equally accessible. Megalodon's life down south would depend on the climate window. Now, if you combine all of this, you get a picture of the Southern Ocean as a place of rhythm. Long daylight feeding seasons, long dark lean seasons, storms that churn the water and shape productivity, ice that advances and retreats, animals arriving and leaving. This rhythm would define what Antarctica felt like during Megalodon's time. Not a constant frozen desert, but a system that pulses. And in that pulse, there is room for a predator to appear when the timing is right. Now, as we move forward, we're going to follow that rhythm into change, because the Miocene did not last forever. The world continued cooling, ice expanded, the Antarctic system became more stable and more extreme, the coastline changed, the water changed, the feeding grounds changed, and those changes mattered for Megalodon, because when the environment shifts enough, even the biggest predator cannot stay the same. So next, we're going to watch the slow arrival of more ice and more permanent change. Not as a sudden disaster, but as a gradual tightening of the world, where the southern seas begin to transform into something that no longer offers the same opportunities. And when that happens, even a giant like Megalodon has to adapt, move, or disappear. The world is never static. It never pauses. Even in places that seem frozen, places like Antarctica, change never stops. It just happens at a rhythm that feels slow to us, but in the context of deep time, it can be swift. When we talk about the slow arrival of ice and change in Antarctica during the time after the ocean was rich with life and Megalodon still roamed the seas, we're talking about a very long story. Millions of years. Not years like you and I experience, but epochs. Time spans so vast that an entire human civilization barely registers as a moment in comparison. Yet that slow sweep of time is the reason Antarctica became the icy world we picture today, and why the conditions that once supported so much marine life eventually shifted, narrowed and transformed. So as you settle into this part of the narrative, imagine not abrupt change, but gradual transformation. Not sudden endings, but the persistent push of colder water, accumulating snow, expanding ice, shifting coastlines, and oceans that quietly but relentlessly rearrange the balance of life. Now, the first thing to understand is this. Antarctica didn't freeze overnight. It didn't snap into existence like a sudden curtain dropping on a stage. It began cooling long before Megalodon appeared, and continued cooling long after it disappeared. The period we've been exploring, the Miocene, was part of this transition, a time when the continent was moving from a milder, more dynamic climate toward the enduring frozen state we know now. Some researchers point to an event near the boundary between the Eocene and Oligocene, tens of millions of years before Megalodon's heyday, when the ice sheets first began to grow substantially. But ice, once it begins to accumulate, tends to feed on itself. Snow compacts into firn into ice. More ice means more reflection of sunlight back into space. Less absorbed sunlight over the surface means cooler local temperatures, which allows the ice to persist. It's a feedback loop, slow but powerful. When ice begins to form on land and push out into the sea as ice shelves, the coastline changes. Where there was once open rock and water, there is now a barrier of ice. Where seasonally open water had supported rich ecosystems, the presence of persistent ice reduces sunlight penetration, alters currents, and changes where nutrients move. What was once a dynamic, productive coastal zone becomes a more restricted location, where life must adapt to cold and ice. In the Miocene, the accumulation of ice was not uniform. There were pulses, intervals where ice advanced more aggressively, and intervals where it retreated or stabilized. This relates to the slow changes in Earth's orbit, tilt and wobble that affect how sunlight is distributed across the planet's surface. These astronomical cycles, known as Milankovitch cycles, act like the deep metronome of climate, pacing long periods of advance and retreat. So imagine Antarctica not as a single state, frozen or unfrozen, but as a continent breathing over millions of years. In some phases it inhales cold, expands ice coverage, and pushes the coastline farther seaward. In other phases it exhales, with ice retreating, exposing more shelf, and allowing open water to persist longer in the year. This is the slow arrival of ice, not a dramatic snap, but a deep, persistent expansion. Now, as ice accumulates, the water that feeds the ocean changes too. When more water is locked in ice sheets, sea levels fall. This exposes continental shelves that once lay underwater. These broad, shallow areas are often biologically productive when exposed, but they also change ocean circulation patterns by reshaping the underwater geography. Currents shift, nutrient pathways change, water temperature gradients adjust, life responds. At first, this may seem irrelevant, certainly not as dramatic a shift as the change from a rich feeding ground for whales to a desolate polar desert. But in the ocean, subtle changes in temperature and currents have outsized effects on productivity. The places where plankton bloom can shift. The timing of blooms can change. The routes whales follow, and the areas they rely on for feeding can drift northward or southward in response. Over millions of years, this alters the entire food web. When the conditions that once supported abundant whale populations near Antarctica change, when the ice cover grows, the open water seasons shrink and the nutrient cycles alter. The prey that supported large predators declines in that region. Whales follow food. Predators follow whales. If the food shifts, the predators must shift too. For Megalodon, this slow progression of cooling seas and growing ice likely meant a gradual retreat from extreme southern waters. Not a sudden disappearance from the map, but a shifting of range into latitudes where the water remained suitable for its lifestyle, where prey was still abundant enough to support its massive size. So you can imagine Megalodon's southern range shrinking over time. In earlier Miocene intervals, it might have ventured farther south during productive seasons. In later stages, as the water cooled more and ice covered more of the coastline, those excursions would become less common, less productive, and eventually unnecessary. And this relocation isn't just a matter of temperature, it's a matter of opportunity. A top predator must follow energy, not geography. And as the energy pulse of the ocean moved, so too would the predator's range. But the story of ice growth is not only about water temperatures and prey availability. Ice itself reshapes coastlines. As glaciers extend into the sea, they carve fjords. They grind down mountains into sediment. They push the land down under their immense weight. They create basins and depressions that will later be filled with even more ice. Every advance of ice leaves a mark on the shape of the continent, on the underwater topography that guides currents, on the shelves where life once gathered. If you could time travel along the shores of ancient Antarctica, you would see glaciers reaching closer to the sea at some times, retreating at others. You would see bays that were once open water become filled with ice tongues and ice shelves. You'd see sediments accumulate where meltwater streams once flowed freely. It's not a sudden sculpture, it's a slow carving. And as the continental ice coverage increased, the ocean became colder and less hospitable for the kinds of life that had thrived in earlier intervals. Sea ice formed earlier in the year and melted later. Open water seasons shortened. Nutrient dynamics shifted as mixing patterns changed. All of this had consequences for the animals that depended on those waters. Whales that once fed near the Antarctic shelf might shift their migration routes. Some species might adapt, others might decline. The abundance and predictability of prey, the very things that made the southern seas valuable to a top predator like Megalodon, would alter. For Megalodon itself, these changes wouldn't necessarily be catastrophic in a moment, but over thousands or millions of years they would mean that the ecological niche it depended on was becoming less available in the far south. More ice means cooler water. Cooler water means changes in productivity. Changes in productivity mean changes in where food is abundant. And if food moves north, predators follow. This is the slow migration of ecosystems across the planet in response to climate change long before humans were part of the equation. It's the planet's own ebb and flow. At the same time, the rest of the world wasn't frozen. Warmer waters still existed at lower latitudes. Tropical seas still supported rich ecosystems. Large sharks could still thrive in those zones long after the southern feeding grounds became less reliable. So as Antarctica tightened its icy grip on the continent, species like Megalodon could remain dominant elsewhere. Following prey toward the equator into temperate and tropical waters, it's a story of contraction, not collapse. Now, this slow arrival of ice also had effects beyond the ocean. It changed weather patterns. It affected the winds that drive currents. It changed how moisture moved around the globe. Antarctica became a cold engine that influenced climates across the southern hemisphere. The continent was no longer just a place on the map. It had become a climate system in itself, and this external influence reshaped the oceans that surround it. So when we talk about the slow arrival of ice and change, we're talking about a shift that rippled across the planet. Not a single moment, but a long, gradual move toward a world that would look very familiar to us today. Cold, icy, and specialized. For the southern seas, it meant less frequent visits from giant predators like Megalodon, not because the shark couldn't exist, but because its world was changing under its fins. The feeding grounds it once used were narrowing. The open water seasons were shrinking. The prey it followed was shifting away. The environment that once supported rich marine life near Antarctica was becoming something else. And in this story, the slow arrival of ice becomes not a sudden villain, but a natural transformation, a chapter in the long life of a planet that never stops changing. And as this chapter closes, not with a bang, but with a long drawing in of colder air, extending ice and shifting seas, we prepare to move into the next part of the story. Because when the world changes enough, even giants must change too. And in the next part, we will look at the most profound consequence of these shifts, why Megalodon disappeared from the Earth's oceans, and how the changing Antarctic system contributed to that final transition. But for now, let the image of that slow ice advance settle in your mind. Not rushed, not abrupt, just persistent, like time itself. Extinction is one of those words that sounds final, even when you try not to let it. It feels like a door closing, like the end of a story, like a single moment when something alive becomes something gone. But in reality, extinction is usually not a single moment. It's a long process where an animal's world becomes less and less compatible with the life it was built to live. It's a narrowing of options, a shrinking of safe places, a steady increase in risk, a slow decline in success. And for Megalodon, the most important thing to remember is this. It didn't vanish because it suddenly became weak. It vanished because the ocean it depended on changed, not in one dramatic shift, but through a chain of changes that stacked on top of each other until the world that once supported it stopped being generous. Megalodon was enormous, it was powerful, it was successful for a long time. That kind of predator does not disappear without reasons that are bigger than the predator itself. So when we talk about why Megalodon vanished from this world, we're really talking about how the planet moved on, and how the ocean's balance shifted away from what Megalodon needed. The first part of that balance is prey. A predator like Megalodon needed large prey, not occasional large prey, but reliable large prey. It needed whales, and it needed enough of them, often enough, in the right places to support a hunter that could not survive on small meals. That's the basic math of being gigantic. If you're small, you can eat small things and stay alive. If you're huge, you need huge energy. And whales provided that energy. During the Miocene, whales were diversifying and spreading. There were many species, many sizes, and many behaviours. That created a rich prey base. But as time moved forward, the whale world changed. Some whale groups evolved into larger, more powerful forms. Others became faster. Some became more specialised in cold water feeding. Some changed migration routes. In other words, the prey did not stay the same. And that matters, because predators and prey are locked in a constant relationship. If prey becomes harder to catch, predators need to adapt. Megalodon had limits. It could bite harder than almost anything. It could overpower large animals, but it could not magically become a different kind of hunter overnight. It was built for certain prey, in certain conditions, so if the whale community shifted toward forms that were less vulnerable, Megalodon's success rate could drop. And when a predator's success rate drops, it doesn't need to drop to zero to cause problems. It only needs to drop enough that the predator struggles to meet its energy needs. Now the second part of the balance is competition. Megalodon did not live alone at the top of the food chain. It lived in an ocean that was becoming crowded with intelligent, social and highly adaptable predators. One of the most important of these was the rise of large predatory-toothed whales. These whales weren't just big, they were smart. They hunted in groups, they communicated, they could coordinate attacks, they could learn. A large shark is powerful, but it hunts mostly alone. A large predatory whale, especially one hunting in a group, can dominate in ways that are not about raw size but about strategy. It can target prey more efficiently, it can protect its young, it can steal kills, it can control feeding grounds. So even if Megalodon was still the largest shark, it was facing a new kind of pressure. A predator that could compete not only for prey, but for space and opportunity. Now, imagine the ocean feeding grounds again. Whales gather to feed in productive waters. That attracts predators. In the earlier Miocene, Megalodon might have had fewer large competitors in some regions. But later, as predatory whales became more prominent, the same feeding grounds could become contested. If a pod of predatory whales arrives, they might not want a giant shark nearby. They might harass it. They might drive it away. They might protect vulnerable prey, like calves, through coordinated behaviour. Even if Megalodon could fight back, fighting is costly. Injury is deadly in the ocean. So a predator that faces more frequent conflict may lose opportunities simply because the risk becomes too high. Competition doesn't have to kill you directly. It can starve you slowly. Now the third part of the balance is climate, and this is where Antarctica becomes especially important. As the world continued cooling, Antarctica's ice expanded and became more stable. Sea ice became more extensive. Open water seasons shrank in some regions. Coastal environments changed. This matters because the Southern Ocean is not just a local ecosystem. It is part of global ocean circulation. As Antarctica became colder and more ice-covered, the ocean currents around it strengthened and stabilised. Cold water spread into lower latitudes. The planet's temperature gradient shifted. This had consequences far beyond Antarctica. Cooling oceans change where productive feeding grounds exist. They change where whales feed. They change migration routes. They change breeding patterns. So climate change wasn't just making Antarctica colder, it was reshaping the entire marine world. For Megalodon, this could be a problem in multiple ways. Cooler water can reduce suitable habitat for a large shark, depending on its physiology. Cooler water can shift prey distributions. Cooler water can alter the timing of seasonal feeding events. So even if Megalodon could tolerate cooler conditions to some degree, the world was still changing around it. And that change was not a one-time event, it was a long trend. Now, think about what happens when whales respond to climate change. They don't stay loyal to a location, they follow food. If productive zones shift, whales shift. If feeding seasons change, migration timing changes. If certain regions become less productive or more ice-covered, whales may feed elsewhere. That means prey becomes less predictable. And unpredictability is dangerous for a predator that needs large meals. Now, another part of the story is sea level. As more water became locked in ice, sea levels dropped. Lower sea levels change coastlines. They change shelf environments. They change shallow feeding grounds. Continental shelves are often where marine life concentrates, because they are shallow enough for sunlight to support productivity, and they are rich in nutrients. If shelf environments change, the entire food web can change. So sea level changes could indirectly affect Megalodon by altering the structure of feeding ecosystems. Now, the next part is reproduction. This is where extinction often becomes unavoidable. A species can survive hard times if it can reproduce successfully and keep its population stable. But if reproduction fails for long enough, the population declines. Large predators often reproduce slowly. They have fewer offspring. They invest more in each one. That makes them vulnerable. If young megalodons depended on warm, shallow nursery areas, and those areas changed due to sea level shifts, climate shifts, or ecosystem changes, then young survival rates could drop. Even if adults could still hunt, fewer young would reach adulthood. Over time, that becomes a collapse. Not a sudden disappearance, but a steady thinning of the population. Now consider another pressure. Smaller sharks and predators could also change. If Megalodon declined, other predators might fill the gap. Great white sharks, or their close relatives, were evolving and spreading during the later part of Megalodon's timeline. Great whites are smaller, but they are highly adaptable. They can hunt a wide range of prey sizes. They can survive in different temperature zones. They can shift diets more easily. A smaller predator has more flexibility. So as the marine world changed, adaptable predators could thrive, while specialized giants struggled. This is one of the most common patterns in nature. Specialists dominate when conditions are stable and favorable. Generalists survive when conditions change. Megalodon was not a generalist in the way a smaller shark can be. It was built for big prey. So when the system stopped supporting big prey in the same way, Megalodon's advantage became a vulnerability. Now, let's connect all of this to the feeling of disappearance. If you were alive in the ocean during that transition, you wouldn't see Megalodon vanish in 1 year. You would see fewer encounters, fewer signs of giant bites on whale carcasses, fewer shadows moving beneath feeding grounds, less of that heavy presence in deep water. The ocean would still be full of life, but the top layer of danger would be changing. Predatory whales might become more dominant, smaller sharks might become more common. The ecosystem would adjust, and Megalodon, the giant that once ruled wide stretches of ocean, would become rarer, until, eventually, it was gone. Now it's tempting to ask for one single cause, one dramatic reason. A meteor, a sudden freeze, a single rival. But that's rarely how these stories work. Megalodon vanished because multiple pressures arrived at once. Climate cooling and ocean changes reduced habitat and shifted prey. Whale evolution changed the prey landscape. Competition increased from intelligent social predators. Nursery habitats may have become less stable. More adaptable predators filled the gaps. Each pressure alone might not have been enough, but together they narrowed the world Megalodon needed. And when the world narrows enough, even the biggest predator can't force it open again. Now here's the part that makes this story feel strange. Even though Megalodon vanished, the ocean didn't become safer. It just changed its kind of danger. The Miocene world gave way to a new marine world, one shaped by different predators, different prey, and a colder, more modern Antarctica. The southern seas became more isolated and more extreme. Whales continued to thrive, but in new patterns. Predators adapted. So the disappearance of Megalodon wasn't the end of the ocean story. It was the ocean turning a page, and Antarctica, with its expanding ice and shifting currents, was part of that turning. Now, as we move forward, we're not going to end this like a closing statement. We're going to drift gently back toward the present, because the best way to understand deep time is to feel the distance between then and now. The Antarctic world of Megalodon's era is gone, but its traces remain. In fossils, in sediment layers, in the shape of the seafloor, in the cold currents that still circle the continent, and if you listen closely, in the way the modern ocean still carries the same kinds of rhythms. Seasonal feeding pulses, migration routes, storm systems, the endless movement of water. So as we return to the present, keep that thought with you. The world doesn't usually change by snapping into something new. It changes by shifting, quietly, until one day you look around and realize the old world is no longer there. Now, without rushing, let's come back. Not by snapping out of the past like waking up from a dream, but by letting the distance close slowly, the way the ocean closes behind a passing animal, leaving no clear trail, just movement settling back into place. Because the world Megalodon lived in is gone, but it isn't unreachable. It's still here in fragments, in layers, in patterns that never fully disappeared, even when the creatures did. So if you're still listening, still comfortable where you are, let's drift forward through time, one quiet wave at a time, until the Miocene fades into the present and Antarctica becomes the continent you recognize again. Picture the Southern Sea first, not as a map, not as a name, but as water. The same water that has always moved around the planet, changing temperature, changing chemistry, changing direction, but never stopping. In the Miocene, those waters carried whales through feeding grounds near the Antarctic shelf. They carried plankton blooms under long daylight. They carried the heavy shadow of a predator that could bite through bone. Now those waters still move, but they carry a different balance of life. The first thing that changes as we drift forward is the cold. It doesn't arrive like a sudden storm. It settles in, it strengthens, it becomes more permanent. Antarctica's ice expands, it becomes thicker, it becomes more stable. Coastal areas that once opened seasonally begin to close more often. Bays that once held open water for longer parts of the year become locked behind ice shelves. The coastline becomes less flexible. Sea ice spreads farther in winter. It melts later in spring. The open water season shrinks, and the ocean responds. Productivity still happens because the Southern Ocean remains one of the most important systems on Earth. But the timing and the shape of that productivity shifts. Feeding grounds change location. The rhythm tightens. Whales adapt. They keep moving. They follow food, as they always have. But the world they move through becomes more extreme. Now, as the ice grows, the continent itself begins to look more like the Antarctica we know. The interior becomes a high, cold plateau. Snow accumulates year after year. Ice flows outward like a slow, heavy river. The land beneath it is pressed down under the weight. The shape of the continent becomes hidden again, not erased, but buried. The coastline becomes an edge of ice more often than an edge of rock, and the sea around it becomes more isolated. The cold current that circles Antarctica strengthens and stabilizes. It becomes a powerful barrier, keeping warmer water farther away. This is one of the reasons modern Antarctica stays so cold. The ocean itself protects the cold, so the continent and the sea begin to lock into the relationship we see today. Now, somewhere along that long drift of time, Megalodon disappears, not with a dramatic scene, not with a final battle, not with a single last moment that anyone could witness. It simply stops being part of the ocean. The teeth stop falling into sediment, the bite marks stop appearing on whale bones. The heavy presence fades from the ecosystem, and the ocean keeps going. That can feel strange to think about, because in our minds, something that large feels like it should leave a larger ending. But nature doesn't do endings the way stories do. Nature does replacement. A predator disappears and another predator takes its place. A feeding pattern changes and another pattern emerges. The ocean reshuffles. So as Megalodon fades out, other hunters rise. Smaller sharks become more prominent. New whale predators thrive. Orcas and other toothed whales eventually become some of the most effective marine hunters on Earth. The danger doesn't vanish, it changes shape, and whales continue to move through the world, adapting as they go. Now, as we keep drifting forward, the ocean becomes more familiar, not because it becomes calm, but because the species begin to look more like the ones you know. Modern whale families take shape, modern seals appear, modern penguins settle into their roles. The Southern Ocean becomes the cold, productive system we recognise, and Antarctica becomes the white continent, a place that looks empty from above, but supports enormous life below. Now, if you could stand on the Antarctic coast today, the difference would be obvious. The air would feel sharper, the cold would feel less negotiable. The coastline would often be ice cliffs and ice shelves instead of exposed rock. The sea would be crowded with floating ice in many seasons. The sky would still have its long days and long nights, because that part never changed. But the light would reflect off ice in a way that makes the world look brighter, harsher, almost unreal. And the soundscape would be different too. You would still hear wind. You would still hear waves. You would still hear ice cracking and groaning. You would still hear whales. But you would also hear something that the Miocene ocean didn't have. The distant noise of modern life, the hum of ships, the occasional engine, the presence of humans at the edges, is not constant everywhere, but it exists now, and it changes the feeling of the ocean. Now think about how the modern Southern Ocean still carries echoes of the old world. Not echoes in a supernatural sense. Real echoes. The same seasonal pulse of plankton blooms under long daylight, the same feeding rush when whales arrive, the same currents that mix nutrients and create life, even the same basic predator logic. Go where the prey goes. That rule didn't disappear when Megalodon did. It still shapes everything. Now, if you want to feel the connection between then and now, it helps to remember what fossils really are. A fossil isn't just a bone in a museum, it's a moment that survived. A tooth falling into sediment and being covered before it could be destroyed. A whale bone sinking to the seafloor and being buried in the right conditions. A layer of mud preserving pollen grains from plants that once lived near the coast. These are small accidents that become evidence, and Antarctica, despite how remote it feels, holds those accidents in its rocks and sediments. Even when most of the continent is covered in ice, the edges and the seafloor still carry records. So when scientists find Miocene fossils in Antarctic regions, they are finding proof that this place once had a different relationship with warmth, with open water, with life. They are finding proof that the Antarctic world was not always sealed shut. And that matters, because it changes the way you look at the present. It reminds you that even the most extreme environments have histories. They didn't start extreme, they became extreme. Now, here's another way the past stays close, in the shape of the ocean floor. The shelf edges, the deep basins, the carved channels, the ridges, all of these features guide currents today. And those currents guide life today. So even though the animals have changed, the architecture of the ocean still carries the memory of older systems. A current flows where it flows because of the seafloor beneath it. A feeding ground exists where it exists because nutrients rise there. A whale migrates where it migrates because the ocean offers food along that route. So the modern ocean is still shaped by ancient geography. Now let's return to the question that started this whole journey. What was Antarctica like when Megalodon was alive? It wasn't the frozen, sealed world you picture when you think of Antarctica today. It was colder than most places, but it was not always locked down. It had open water seasons that could stretch longer in warmer intervals. It had coastlines that could be more exposed. It had feeding grounds that could draw whales south. It had storms and long light and dark seasons, just like it does now, but the balance was different. And in that balance there was room for a giant predator to pass through the southern seas, not as a myth, not as a rumour, but as a living animal following prey. Now, if you let that idea settle for a moment, it can change how you see the modern world, because Antarctica today feels permanent. The ice looks eternal, but it isn't. It's the current state of a system that has changed before and will change again. The ocean has always been a place of movement, and the planet has always been a place of adjustment. Now, take a breath, wherever you are. Notice the room around you, the weight of your body resting, the sound of your own environment, and remember that while you're sitting here, the Southern Ocean is still moving, waves are still forming, currents are still circulating, whales are still migrating, ice is still shifting and cracking. The world is still doing what it has always done, changing quietly while life continues. And somewhere, in sediment far beneath the sea, there are still teeth. Not moving, not hunting, not part of the living ocean anymore, but still present as proof that this world once held something enormous, something real, something that lived and fed and travelled through the same planet you live on now. So as you let this story fade into the background, let it fade gently, not as an ending, but as a return, back to your own time, back to your own night, back to the present, carried in slowly, the way the tide carries in and out, without needing to explain itself.